Hey guys, tonight we drift right up to the very skin of the sun, where light is so bright it feels like it could peel the paint off your thoughts. You're hovering above a surface that isn't really a surface, watching boiling arcs of plasma fling themselves upward like slow-motion geysers. If you reached out, don't do it by the way you'd touch a furnace so intense that even atomic bonds panic and fall apart. And yet, in this terrifying beauty, something surprisingly gentle begins the sun's breath. A soft, continuous exhale that spreads across billions of kilometers. It's the quietest thing you'll never experience, because standing here, you probably wouldn't survive long enough to brag about it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And tell me where you're listening from and what time it is right now. I love seeing the constellation of little lights across Earth. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You hover weightless above the roiling solar corona, as if someone gave you front row seats to the universe's most dramatic simmering pot. You can feel not with skin, but with imagination, the first wisps of the solar wind lifting off. They don't roar or surge, they simply drift, escaping the sun like heat leaving a hot sidewalk at the end of a long day. And you follow that movement leaning forward into the exhale. This is where the sun's quiet exhale begins, a place where atoms are so hot that they stop caring about staying home. A mainstream fact, the corona reaches more than 1,000,000 degrees Celsius, far hotter than the sun's visible surface. Nobody fully understands why this happens. Scientists still argue whether tiny magnetic explosions heat it, or whether waves from deeper inside shake it, like a cosmic stovetop. Either way, you're floating there like someone who wandered into the wrong sauna but is too polite to leave. Below you, magnetic loops tower like glowing cathedral arches, trapping plasma until they snap and fling it outward. Every so often, one spits a jet of particles into space that feels like a sneeze from a deity fast intense, and definitely not socially distanced. But the normal state of things isn't explosive. It's steady, endless, like the sun breathing out through its teeth. You feel that flow tug on you, even though it's made of particles so sparse that a cubic meter has fewer atoms than a good sneeze. But they're fast, really fast, hundreds of kilometers per second, sometimes more, moving like a silent crowd leaving a stadium. A quirky tidbit scientists love to mention: if you could somehow bottle a liter of the solar wind at Earth's distance and bring it home, it would contain fewer particles than the air trapped inside a sealed potato chip bag. Yet out here the wind is everything. It shapes planets, sculpts space, and defines the borders of the solar system. You glide outward a bit more and now you can feel the tug of magnetic fields, twisting and threading like invisible ropes. They guide you the way currents guide a leaf in a river. And you realize the sun isn't just breathing out, it's braiding its breath into patterns that stretch across billions of kilometers. As you float, the light dims just a little, not because the sun has changed, but because you've stepped into a karma patch. It's like finding the quiet corner of a crowded room. The particles drift past you with a kind of sleepy determination. They're ionized, charged, electrically noisy, but from your vantage point they seem serene, almost shy. If they had emotions, this would be the part where they whisper I should go before slowly moving toward the door. The solar wind begins its journey right where you're hovering, and you can sense it's not one uniform stream. It has moods. When the sun is calm, the wind blows like a steady breeze, perfect for a sunset walk. When the sun is cranky, and it often is, the wind becomes a jittery, irregular flow that slaps planets around. Somewhere in the back of your mind, you realize this plasma isn't just moving. It's carrying pieces of the sun's magnetic personality with it. Every little wave and wobble, every twist and braid, all of it travels outward like gossip traveling through a crowded cafe. Scientists still argue whether the solar wind starts because of pure heat pressure or complicated magnetic shenanigans. Some say particles just get so energized they simply drift away. Others swear it's the sun's magnetic fields flinging them off like someone shaking water from their hands. The truth is probably a mix, like most things in cosmic life. You float higher, letting yourself be carried by the upward swell of particles, and a new sensation creeps over you, the feeling of speed without motion. It's the odd paradox of drifting in something fast. The solar wind is accelerating you, but everything around you is also moving, so it feels like you're suspended in an invisible escalator that gently rises without shaking. For fun, you picture the sun wearing a tiny fan-shaped mask, breathing into the entire solar system like a tired marathon runner. That's your third light joke, but honestly the image will stick with you. The first wave of the solar wind catches you, fully lifting you into the flow. The corona glows below you, not like fire, but like the world's brightest fog. Every shimmer is a particle gaining its freedom. Every flicker is a doorway opening, and you cross the threshold. Here at the very start of the wind's journey, you become part of the sun's quiet exhale. You're carried outwards slowly at first, ready to follow this cosmic breath as it stretches from the glowing furnace behind you all the way to the frayed drifting edges of the solar system. You drift farther into the flow, letting the sun shrink behind you, until it feels less like a blinding presence and more like a warm pressure at your back. The solar wind thickens here, but thick is relative. You're swimming in a river so faint that you could travel 1,000,000 kilometers and barely bump into anything. Yet strangely you feel surrounded, because this wind is made of ghosts. Charged particles, mostly electrons and protons, slip past you, like translucent sparks so small and so fast that they barely register, except as a soft tingle in the mind's imaginary fingertips. They don't glow out here. There's no cinematic sparkle, no Star Wars hyperspace streaks. Just the subtle pressure of movement. If space had a breath, this would be it. A gentle suggestion of direction, like the faint push you feel when someone walks by too close. Scientifically speaking, these atoms were once part of the sun itself. They lived their whole lives in the furnace of fusion, squeezed together under unimaginable pressure, and then one day they found a gap, a weakness, a moment where gravity lost its grip for just long enough, and they slipped free. Not dramatically, not heroically, more like interns sneaking out of a boring meeting while the boss isn't looking. A mainstream fact the solar wind is constantly escaping, because the sun's gravity simply can't hold on to these high-energy ions once they reach the corona's 1,000,000-degree temperatures. You let the flow carry you, and the sensation is oddly peaceful. No buffeting, no turbulence, just an endless outward drift. You feel like a bubble in a carbonated drink, rising without urgency. But make no mistake, these particles are hauling. Some reach 700 kilometers per second, meaning they'd cross the distance from Los Angeles to New York before you could even complain about airplane legroom. A quirky tidbit: if you somehow scooped a handful of the solar wind near Earth and tried to breathe it, you'd suffocate instantly, but technically from lack of particles, not their danger. Imagine inhaling an atmosphere so empty, it makes a vacuum cleaner bag look dense. Yet despite this emptiness, the solar wind fills every corner of the solar system. You can almost see it now, not with eyes, but with a sense of pressure. It pushes against everything: planets, comets, dust, magnetic fields, even the imaginary bubble of space itself. In a slow, steady beat, it changes the shape of everything it touches. As you drift outward, your body, physical or imagined, feels the particles passing. They're so sparse you could stand here forever and not get hit enough times to count on one hand. But over cosmic distances, their influence is absolute. They carve space like a river carves canyons, not quickly, but relentlessly. Scientists still argue whether to think of the solar wind as a fluid or as a cloud of individual particles. Some swear it behaves like water flowing around rocks. Others insist it acts more like a swarm of bees, each doing its own thing, but moving in roughly the same direction. The compromise is usually plasma with personality, which is honestly my favourite physics phrase of all time. You drift sideways in the flow, watching the density change like weather. In some patches, the wind feels like a soft drizzle. In others, like a near-total emptiness, where it's hard to believe anything moves at all. The variation is subtle but real. It's caused by magnetic turbulence, and the sun's rotation, which occasionally bunches and stretches the wind the same way traffic bunches and stretches on a freeway. Except in this case, nobody's cutting you off at 700,000 mph, so that's nice. Another joke sneaks in: if road rage existed in the solar wind, it would probably just be two particles passing within a few kilometers of each other and saying, "Wow, personal space buddy, the sun keeps shrinking behind you." You're tens of millions of kilometers out now, and the wind feels fully formed, a genuine cosmic breeze. Not an explosion, not a storm, just a steady, unstoppable exhale made of tiny, fast-moving ghosts. They don't collide much out here. There's too much room. Each particle travels like it believes it's the only thing in existence. Every once in a while, you imagine them wearing tiny sunglasses and saying, "I'm not like the other particles." A fun fact floats up from some sleepy corner of your brain. The solar wind creates something like the sun's personal bubble, a heliosphere pushing back against the entire galaxy. You're inside that bubble now, drifting in the breath of a star that doesn't stop breathing even for a millisecond. This wind never pauses, never reverses, never takes a day off. If the sun had a HR department, it would be thrilled. You turn your attention outward, feeling the wind spread into every direction. This is the moment you realize something profound. The solar system isn't empty. It's not even close. It's filled with a continuous outpouring of particles that touch every world, every moon, every pebble drifting in orbit. Even the most distant Oort cloud objects feel this breeze faintly, like someone blowing across a candle from another room. The particles continue drifting past you, each carrying a trace of the sun's magnetic field. Tiny magnetic fingerprints. They twist, wiggle and shift, changing their alignment like invisible dancers, choreographed by the star behind you. This magnetic imprint affects everything it meets, from Earth's auroras to country tales to how electronics behave on spacecraft. You start to feel the subtle curvature inside the wind. The particles aren't just moving straight outward, they're being dragged sideways by the sun's rotation. You're beginning to sense the first hint of the Parker spiral, an entire solar system shaped not by gravity or light, but by the slow, steady swirl of a star turning on its axis. But you're not there yet. For now, you're still in the heart of the ghostly wind, drifting through a stream so calm and so continuous that you almost forget how alien it is. The sun's breath has claimed you, and it's carrying you outward to places where space stops feeling empty and starts feeling alive. You drift farther into the flow, and the sensation changes subtly at first, like a shift in the tempo of music you didn't realize was playing. The solar wind, which felt like a gentle outward breeze a moment ago, begins to tug you not just away from the sun, but sideways. It's like trying to walk in a straight line while a slow, invisible carousel spins beneath your feet. You're entering the Parker spiral. You don't see the shape directly. This isn't a neon light coil floating in space, but you feel it. The particles slip past you with a strange slant, angled in a way that hints at something enormous happening behind you. The sun's rotation, which takes about 27 days at the equator, drags its magnetic field along with it, stretching that field out into space like taffy. The solar wind doesn't move instantly. It takes time to travel outward. So as the sun spins, the wind gets pulled into a spiral somewhere between a whirlpool and a cosmic soft-serve cone. A mainstream fact, this structure predicted by Eugene Parker in the 1950s, was so controversial that scientists told him his math could not possibly be real. The universe as usual backed Parker. You shift slightly, letting the magnetic field nudges guide you. The feeling is strange, but almost pleasant, like someone gently steering you through a crowd with a hand on your shoulder. The magnetic lines curve, bend and elongate, and you can sense their pull. The farther you drift, the more the wind's movement becomes angled, and the clearer the spiral's shape becomes in your mind. A quirky tidbit. If you could draw the Parker spiral big enough to hold in your hand, it would look almost exactly like the pattern on old rotary phone cords. Congratulations, you're basically traveling through a 1950s desk accessory made of ionized plasma. Scientists still argue whether the Parker spiral is smooth or choppy on small scales. Some say it's like a neatly combed hairstyle. Others claim it's more like bedhead at interplanetary distances, all messy ribbons and tangled knots. The truth is probably somewhere in between a cosmic hairdo that starts tidy and gets progressively chaotic as it stretches outward. You drift deeper, feeling the magnetic field lines whip past you in long, gentle arcs. They aren't static. They flutter with turbulence, vibrating with waves that ripple through them like a shaken jump rope. These waves can be fast or slow, sharp or fuzzy, sometimes predictable, sometimes utterly chaotic. If this were a soundtrack, you'd be hearing a constant rumble layered with faint whispering static. Another light joke slips in: if GPS signals ever developed anxiety, this magnetic turbulence would absolutely be the cause. The spiral shape becomes more intuitive as you move. You lean your imaginary weight forward and the solar wind gently bends your path, pushing you into an arc. You're being threaded through the spiraling lanes of the sun's magnetic influence, almost like being on a slowly turning lazy river ride, except the water is electrified and traveling hundreds of kilometers per second. You pass through a region where the wind suddenly speeds up. These high-speed streams originate from coronal holes, dark cooler regions on the sun's surface, where magnetic fields open outward like chimneys, letting particles escape more freely. When these fast streams catch up to slower wind ahead of them, they create compressed regions called co-rotating interaction regions, CIRs, space weather's version of traffic jams. You feel now a gentle yet unmistakable pressure change, like drifting into a warm front. Nothing violent, yet just a subtle thickening of the wind. These regions can sometimes create storms that affect planets, but here at this early spiral stage, they're just part of the normal landscape. You drift onward, and the spiral becomes even more pronounced. The magnetic field lines around you now angle almost sideways, pulled nearly horizontal by the sun's rotation. The farther you go, the tighter the curve. If you let go metaphorically, you drift in a long curling path that never stops bending. A fun, almost poetic realization hits you: every planet in the solar system lives inside this spiral. The magnetic fingerprints of the sun reach everything: Mercury, Earth, Jupiter, even the far-off Kuiper belt. You're moving within the same structure that shapes the auroras, steers energetic particles, and determines how solar storms travel. And in this spiral, you start noticing something else. The wind isn't just charged particles, it's carrying information. Every wobble, every ripple in the magnetic field tells a story of solar activity. During quiet periods, the spiral is smooth. During active periods, it's chaotic, twitching with storms, shocks, and bursts of turbulence. Scientists still argue whether these ripples can be used to predict solar flares or whether the sun prefers to keep its tantrums private. The evidence is mixed. Like most things in astrophysics, the universe refuses to hand us a clean instruction manual. As you float, the sun's rotation continues shaping the wind behind you. You can almost feel the slow twist, like the gentle turn of a massive clockwork device. Every moment, the sun winds another thread of magnetic field into the spiral, sending it outward into the dark. One more light joke lands: if the sun were a baker, the Parker spiral would be its infinite cinnamon roll. You drift through a thick region of angled fields, feeling the spiral's force gently tugging at your imaginary coat. The entire structure is enormous beyond comprehension, stretching billions of kilometers, curling through every orbit, shaping the outer boundary of the solar system. And you're riding it like a leaf caught in a cosmic swirl. The further you go, the more obvious it becomes. You're not just leaving the sun. You're following the path carved by its breath, twisted by its rotation, etched into space as a massive spiral highway. You inhale gently because it feels appropriate, and let the wind carry you deeper into the curling structure. Ahead of you, new shapes in the magnetic field begin to shimmer. Waves, expansions, and the first hints of something more violent waiting farther down this spiral track. But for now, you drift spiraling outward, guided by the slow-turning heartbeat of a star. You drift along the curling magnetic lanes of the Parker spiral, letting the wind guide you like a leaf on a cosmic tide. Everything feels calm, almost sleepily so. The particles whisper past in their endless outward stream, and for a moment you imagine that this journey might stay peaceful forever. And then the sun clears its throat. The solar wind around you shifts not violently, but with an unmistakable change in pressure. It's like stepping from a quiet hallway into a room where everyone suddenly stopped talking. Something is coming. The calm river you've been floating in is about to meet the chaotic edge where storms are born. Behind you, though, distance works strangely out here. You sense the flare before you fully feel it. A spike in brightness, a sharp twist in the sun's magnetic field. A pulse of energy that surges through the spiral like a rumor traveling at light speed. Solar storms on your neck. The solar wind doesn't stay gentle forever. Sometimes the sun spits out bursts of plasma called coronal mass ejections, CMEs, the cosmic equivalent of a sneeze from a star having a bad day. Flares and CMEs can combine into events so powerful that Earth's magnetic field hums like a stressed violin string. You're about to feel one of those gusts now. A mainstream fact, a CME can throw billions of tons of charged particles into space at speeds over 2,000 kilometers per second. They can expand to sizes larger than Earth's orbit. A literal, planet-sized cough. You feel the first wave hit you not as impact, but as pressure, an invisible hand pushing your back, urging you to accelerate. The particles around you grow denser, the turbulence stronger. The magnetic field lines you've been following twist tighter, vibrating like plucked strings. You're in the path of an accelerating blast of solar plasma. And in the middle of this cosmic chaos, you can't help thinking, well, this escalated quickly. The CME front washes over you, and it's both intense and eerily silent. No roar, no flash, just speed. A rising river of charged particles compressed into a shockwave that marches outward like a fast-moving weather front. The magnetic field in the region flips orientation, turning like a doorknob, and you feel the rotation in your imaginary bones. A quirky tidbit: during a strong solar storm, astronauts in deep space would see flashes of light inside their eyes, even with their eyes closed. The particles pass straight through their retinas and trigger phantom sparks. Basically, space gives you hallucinations whether you ask for them or not. The CME wraps around you, now pushing everything forward. You're caught in its flow like a leaf in a sudden gust. The spiral pattern you followed earlier becomes distorted, bent by the event's sheer force. Magnetic field lines snap, reconnect, and twist into new shapes around you like cosmic spaghetti being tossed in a pan. Scientists still argue whether reconnection in these storms happens through large-scale magnetic folding or tiny explosive knots called plasmoids. Either way, it's chaos. Beautiful, structured chaos. You glance metaphorically to your left, or whatever direction counts as left, in a wind made of particles and notice something incredible. The CME isn't uniform. It has cavities, knots, and waves, clouds within clouds. Some are dense as a storm front, others are so thin they barely exist. It's as if the sun threw a handful of glitter and smoke into space, and the mixture is still swirling. You feel the direction of the blast shift pushing you sideways. This is the magnetic field's doing. Your invisible road is being repaved in real time. The sun's rotation, its magnetic pulse, and the CME's momentum all collide here, forming a labyrinth of currents and swirls that tug on you unpredictably. And then suddenly the storm exposes something else: how the solar system protects itself. Ahead of you, the spiral begins to flatten, angled by the shock front. Farther out, Earth lies somewhere along this highway, and whether this particular blast hits the planet or glances off depends on timing, geometry, and luck. Earth's magnetic field is a shield, a bubble that stands ready to take the hit so the surface doesn't fry like an unfortunate piece of toast. But even then, Earth isn't invulnerable. Strong CMEs have caused power outages, disrupted satellites, and once made telegraph systems in 1859 spark and burst into flame. Imagine trying to explain that in a Victorian newspaper. Another light joke slips in: if your Wi-Fi ever drops randomly, you can always blame the sun. It's not always true, but it's a satisfying excuse. You're still inside the CME, feeling its intensity wane slightly as the blast spreads outward. Anything that expands across millions of kilometers inevitably thins out. But don't underestimate it. The shock is still strong enough to warp magnetic fields across planetary distances. Every few seconds you feel a new ripple, a wave of charged particles, or a pressure shift that nudges you like a sleepy cat pawing at your leg. The Parker spiral around you shivers with the disturbance. The neat, elegant curves become jagged. Some regions compress while others stretch. The spiral will recover, but the memory of the storm will ripple through it for days. As the CME continues past you, the very last edge brushes your back like the trailing end of a warm wind, and just like that, you're back in calmer solar wind again. Not completely calm storms leave echoes, but calmer compared to the blast you just rode. You drift forward, letting the magnetic field settle around you. The particles resume their quieter outward flow, carrying faint traces of the storm with them like lingering perfume. The sun is behind you again, its tantrum fading, and a gentle breeze resumes. Your journey continues. Ahead lies a structure built of magnetic threads and plasma pockets, a place where bubbles sit inside bubbles shaped by the sun's invisible hand. But for now, the storm has passed, and you float forward in the quiet wake of something impossibly big. The storm fades behind you like the last echo of a drumbeat, leaving a restless stillness in its wake. The solar wind is calmer now, but not the same as before. There's a subtle tremble in the flow, a leftover shiver from the CME's passing. You drift through it like someone walking through a room. Right after an argument, the air feels normal, but you can tell something happened. As the tension unwinds, the magnetic field around you begins to settle into new shapes that don't quite match the elegant Parker spiral you rode earlier. Instead, you start noticing pockets forming in the plasma, regions where the density changes, magnetic loops that seem to pull inward, bubbles forming inside bubbles. You're entering one of the strange regions sculpted by the sun's magnetic field, vast magnetic balloon structures that inflate and collapse like breathing organs in the solar wind. The sun's magnetic field is not a simple dipole like Earth's. It's a tangled forest of field lines, constantly stretched, twisted, and reconnected by solar rotation and plasma motion. Near the sun, the magnetic field is structured and intense, but as it expands outward, it begins to fragment into isolated magnetic flux tubes. That's the official term, but honestly they're magnetic bubbles, enormous ones, some big enough to swallow Earth whole without noticing. A mainstream fact, the solar wind is filled with these flux tubes, magnetic pockets where the field lines link back on themselves like cosmic soap bubbles. You glide into one now, feeling the shift immediately. Inside the bubble, the solar wind density changes. The particles drift more slowly, almost lazily. You feel as if you've stepped into a warm pocket in a cold ocean. The magnetic field lines wrap around you like a loose cocoon, giving the space a strangely enclosed feeling despite being a vacuum. For a moment, you get the ridiculous impression that you're floating inside a gigantic, transparent hamster ball. A cosmic stress ball the sun squeezed out in a moment of magnetic tension. Scientists still argue whether these flux tubes form near the sun and expand outward, or whether they coalesce naturally as the solar wind moves through space. Some argue they're remnants of magnetic patches on the sun's surface. Others claim they're born from turbulence and spontaneous reconnection far from the sun. The debate continues politely unless someone's had too much conference coffee. In one corner of the bubble, well, bubbles don't technically have corners, but your brain insists on labeling it that you see a faint shimmering. Plasma swirling around magnetic lines. They're reconfiguring, reconnecting, snapping, and joining like microscopic lightning. Tiny bursts of energy spark off, none big enough to harm, all big enough to notice. A quirky tidbit. When magnetic reconnection happens in the solar wind, the energy release is so small that a human would never feel it. But scaled up across billions of kilometers, reconnection helps power auroras, radiation storms, and even atmospheric escape from planets. Space weather runs on tiny sparks that add up to cosmic consequences. You feel one such spark now, a little kick like someone bumping the back of your chair. The bubble begins to shift around you, expanding slightly. The magnetic field lines ripple like the skin of a drum being gently tapped. For a moment you drift near the bubble's boundary. Outside, the solar wind flows more quickly, stretched and angled by larger-scale fields. Inside, it's calmer, cushioned. You realize the bubble is moving too, not independently but carried along with the wind. Like a leaf trapped in an eddy, swirling but always drifting outward. You float through a thin region between bubbles, a magnetic boundary so sharp it feels like crossing a faint membrane. On one side, calm flow. On the other, a twitchy, faster breeze carrying echoes of the recent CME. The contrast is startling. It's the solar wind equivalent of stepping from a quiet library into a noisy street. Then you cross into the next bubble. This one is larger, stretched by turbulence into a kind of elongated oval. You sense its magnetic spine field lines, looping and twisting like soft springs. In some places they bunch together tightly. In others they spread apart in a feather-like pattern. These variations shape the plasma flow, redirecting particles like a garden hose, bent by invisible hands. Inside this bubble you feel a strange drifting sensation, like gravity is trying to exist but can't quite remember how. The magnetic pressure increases slightly. Particles slip along the field lines, moving in spirals rather than straight paths. Everything is organized, subdued, almost sleepy. A light joke surfaces in your mind: if the sun had a filing cabinet, these bubbles would be its badly organized folders. You float along the magnetic curvature, tracing the loops as they bend away from the sun. These bubbles are temporary, some lasting hours, others weeks. They merge, divide, stretch, collapse. Motion is constant but gentle. Nothing here is static. Outside the bubble, you sense the wind thickening again. The Parker spiral is asserting itself, guiding the plasma along its curved highway. The bubble begins to thin, its magnetic walls relaxing. You drift outward naturally, crossing its fading boundary, into the regular wind once again. Behind you, the magnetic pocket slowly dissolves. Ahead of you, more bubbles shimmer, some small, some enormous, some so faint you can barely sense them at all. They form a layered structure inside the solar wind, like pockets of air inside a loaf of rising bread. The sun's breath isn't smooth, it's textured. It isn't uniform, it's quilted. It isn't simple, it's fractal, alive, full of hidden folds and shifting patterns. You drift forward past bubbles and pockets toward the region where planets begin to push back, where their own magnetic shields rise to meet the solar wind like invisible faces pressed against an invisible gale. That boundary is waiting for you now, growing clearer with every drifting second. You drift onward, and the solar wind, still warm with the aftertaste of magnetic bubbles, begins to meet resistance. Subtle at first. a faint pressure change like walking into a barely perceptible breeze that wasn't blowing a moment ago. You're still within the sun's exhale, but now the flow is no longer alone in shaping space. It has reached the zone where planets breathe back. Here the solar wind stops being the unquestioned sculptor and starts being shaped in return. Every planet with a magnetic field, even a faint one, pushes against the sun's breath. Some push hard, some barely push at all, but every world shielded or not leaves an imprint in the wind. You're about to drift through those invisible fingerprints. Ahead of you, a magnetic obstacle begins to appear, not visually, but as a tension in the plasma. The solar wind particles slow and bunch, piling up like water against the bow of a ship. You feel the pressure build across the entire front and the wind begins to curve around it. This is the bow shock the shockwave created when the solar wind encounters a planetary magnetic field. A mainstream fact, Earth's bow shock, for example, forms at about 90,000 kilometers upstream from the planet, where the solar wind first slams into the magnetosphere. That shock heats, compresses and redirects plasma, forming a protective buffer. You drift through a generic bow shock, now not Earth's, not any specific planets, but the concept made real. The solar wind transitions abruptly from supersonic to subsonic, and the change feels like someone switched the current beneath you. One moment you're riding a fast-moving breeze, the next you're in stirred, churning waters. Turbulent, rumbling, uneven. It's a bit like being inside a cosmic washer set to gentle cycle, except gentle here means plasma waves colliding at hundreds of kilometers per second. But you keep your composure. At this point, getting tossed around by invisible shock waves is practically your new hobby. Scientists still argue whether bow shocks are stable structures or flickering, ever-changing layers shaped by micro-instabilities. Some spacecraft have crossed the boundary multiple times in just minutes, suggesting the shock can fold and ripple like a giant magnetic bedsheet in a storm. Behind the bow shock lies the magnetosheath, the region where the slowed solar wind struggles to navigate the magnetic pressure ahead. Think of it as a traffic circle where nobody knows how to merge properly. Plasma eddies whirl around each other, magnetic field lines pile up, density fluctuates wildly. You drift through it, feeling the wobbling magnetic turbulence, as if someone is tapping your shoulders from all directions. A quirky tidbit in the magnetosheath around Earth, we've detected mirror-mode wave structures that look like magnetic Swiss cheese, with alternating pockets of high and low magnetic field strength. If space had a snack aisle, this would be it. As you move deeper, the planet's magnetic field makes its presence known. You feel tension in the lines around you, direction, shape, structure. The solar wind is no longer in charge. It's being redirected, forced to bend around an invisible obstacle. You hover at the outer boundary of the magnetosphere, the magnetopause. This is the place where a planet's magnetic field pushes back hard enough to carve out a protective bubble in the solar wind. Outside turbulent plasma, inside a calmer shielded region where the planet's own magnetic field dominates. At this invisible wall, the solar wind comes to a halt, not literally, but dynamically. Pressure from the solar wind equals magnetic pressure from the planet. It's a stalemate, a cosmic handshake with a little arm wrestling mixed in. You reach out figuratively and feel the boundary flex beneath your touch. The magnetopause isn't rigid. It wobbles, ripples, expands, contracts. During strong solar storms, it can be shoved so far inward that it compresses close to low Earth orbit. During calm times, it relaxes outward, like someone stretching after a nap. Another joke drifts through your mind. If planets had personal space bubbles, this would be theirs, and the solar wind is the annoying neighbor who keeps knocking on the door. You glide along the magnetopause, following the curve of the planet's magnetic boundary. Every few moments, you feel tiny jolts, magnetic reconnection events. These are brief link-ups where the solar wind's magnetic field merges with the planetary field, letting particles sneak across the boundary like students slipping through a cracked classroom door. Some reconnection events are gentle. Others, they unleash storms that whip energy deep into the magnetosphere, powering auroras, substorms, and eerie electric currents that circle the planet like neon tattoos. Scientists still argue whether reconnection at the magnetopause happens in thin extended sheets or chaotic fractal knots. Spacecraft have seen evidence for both, leaving the debate deliciously unresolved. You continue drifting along the magnetopause, sensing how each planet reshapes the solar wind differently. Some magnetic fields are tilted, creating asymmetric boundaries. Some are offset from the planet's center, producing weird lopsided shapes. And some planets, like Mars, barely fight back at all, letting the solar wind strip away their atmosphere like peeling paint off an abandoned house. But Mars will come later. For now, you're here learning the basic dance steps wind pushes, planets resist, and the boundary forms wherever the pressures meet. As you ease forward, a new sensation grows ahead, a particularly strong, stable magnetic bubble. You're approaching a world whose magnetosphere doesn't just push back. It creates shimmering shields strong enough to turn solar tantrums into glowing sky paintings seen from the surface. That world is next on your path, and its protective bubble is waiting for you like a shimmering doorway carved into the wind. You drift toward the shimmering magnetic doorway ahead, letting the solar wind guide you like someone being carried by a lazy river toward a sudden breathtaking waterfall, not dangerous, just majestic in scale. The pressure of the wind thickens again, but this time there's a softness to it, a sense of structure forming beneath the flow. You're approaching a world that refuses to be shaped passively by the sun's breath. Instead, it bends that breath away from itself in an elegant, continuously shifting dance. Earth's magnetosphere. The first thing you feel is the bow shock, again familiar yet distinct here. The solar wind slams into the region in front of Earth's magnetic field, slows down, abruptly heats up, and swirls like water forced to rush around a stone in a stream. You slip through the shock with a gentle lurch, as if stepping down a single stair you didn't notice. Then you enter the magnetosheath, that thick buffer of turbulent plasma between the shockwave and the magnetosphere. It feels busy, lively turbulence rattling magnetic field lines, particles tumbling in eddies. A cosmic waiting room where the solar wind's chaos must settle before confronting the planet's magnetic defenses. You glide through it, all feeling the electric hum of the region. Tiny fluctuations pepper your awareness like faint static when a radio isn't quite tuned. Magnetic waves ripple through the plasma, bending, folding, snapping back. There's a restless energy here that never fully sleeps, and then finally you touch the boundary itself, the magnetopause, the outer skin of Earth's magnetic shield. It yields the moment you brush against it, not weakly, but elastically. The surface wiggles like a soap bubble when tapped. The solar wind pushes from outside, the planet's magnetic field pushes from inside, and you're floating right where the two forces balance perfectly, as though held between two invisible hands. A mainstream fact, Earth's magnetopause usually sits about 10 Earth radii from the planet on the day side, but during strong solar storms it can be squashed to half that distance. Entire satellites have found themselves suddenly outside the magnetosphere during such compressions exposed to raw solar wind, like someone walking outside without checking the weather. You skim the magnetopause and now you feel the ripples, the Kelvin-Helmholtz waves, great rolling curls generated when the solar wind shears past the boundary. They're enormous, some stretching tens of thousands of kilometers each wave, crest curling like a cosmic surf break. If you could stand on one, you'd ride a magnetic tsunami. A quirky tidbit spacecraft have detected literal plasma vortices in these waves, spinning tubes of charged particles shaped like giant cinnamon rolls, drifting across the boundary. So yes, in a way, the Earth's shield occasionally gets covered in cosmic pastry spirals. But beneath this playful imagery lies a very real process, magnetic reconnection. You feel it now, small jolts, where solar wind magnetic fields link with Earth's field lines, creating tiny transport doors. Through each reconnection site, particles leak inward. Not many, but enough to matter. Scientists still argue whether reconnection happens steadily along long sheets, or explosively in short scattered bursts called flux ropes. Spacecraft missions like MMS have caught glimpses of both, leaving the debate very much alive and very passionately caffeinated. You slip through one such reconnection spot. It's not dramatic, more like stepping through a soft curtain that brushes your shoulders, or in this case your imaginary plasma-sensing soul. Inside, the environment shifts immediately. The chaos outside softens into something structured, almost geometric. Earth's magnetic field lines sweep around you like invisible beams curving from pole to pole. You're no longer drifting freely. You're being guided, channeled along magnetic arcs. It feels like entering a cathedral made of force fields instead of stone. This is the magnetosphere proper. Here the solar wind can't simply rush as it pleases. It must navigate Earth's magnetic architecture, loops and arcs and long stretched tails. Space here is calmer but not serene. Even the quiet has structure. You float along a field line that curves toward the night side, sensing the tension as the magnetosphere stretches into a comet-like tail behind Earth. and somewhere deeper inside the system, the part you're drifting toward now, that magnetic tension begins to break and heal in cycles. That's where substorms come from. But you're not there yet. For now, your attention is drawn to a subtle shimmer near the polar regions, a softness, a glow forming not in visible light yet, but in the behavior of the plasma. Particles leak in through reconnection sites, stream down magnetic funnels, accelerate rapidly, and spiral inward like raindrops sliding down a window. You know where those particles are heading, you know what they'll create. You drift closer to the polar cusp, a funnel, where solar wind can slip almost directly into the atmosphere. It's an opening a throat in Earth's magnetic armor, and as you look downward more with imagination than eyes, you sense faint whispers of energy sliding toward the upper atmosphere, ready to paint the sky. Auroras. But that's the next step of your journey. Right now you're suspended on the edge of the shield itself, feeling the planet breathe out its magnetic strength and breathe in the solar wind's particles, creating a dance that shapes everything from satellite orbits to the quiet flicker of lights over an Arctic winter sky. You drift forward, letting the funnel guide you toward the shimmering curtains waiting below. You drift down the magnetic funnel like a leaf caught in a slow, spiraling whirlpool. The lines of force pull you inward, not harshly, but with the gentle inevitability of gravity guiding a raindrop toward the ground. You're entering the region where the sun's breath meets Earth's upper atmosphere in one of the most beautiful collisions nature ever invented, the auroral zone. Up here, hundreds of kilometers above the planet, the air is so thin it barely counts as air at all. But it's enough for incoming charged particles to crash into atoms and molecules, exciting them into brief glorious shimmers of light. You don't see the glow yet. You feel the potential for it, like the faint buzzing you get just before a neon sign flickers on. A mainstream fact auroras are caused when energetic electrons and protons from the solar wind spiral down Earth's magnetic field lines and strike the upper atmosphere, exciting oxygen and nitrogen atoms. Oxygen glows green or red. Nitrogen glows blue or purple. Nature is basically doing physics-based LED art. You drift lower, and the first hints of colour appear, not full curtains yet, but wisps, strokes, soft trails like someone brushing invisible paint across the sky. The particles around you begin to accelerate, whipped along by electric fields that form naturally in the magnetosphere. You feel the speed pick up, a tingling sprint of electrons racing past you, eager to meet the atoms waiting below. And then it happens. A gentle green shimmer blossoms beneath you, spreading like the first ripple in a pond. Then another, and another. The sky starts breathing light. You descend toward the glowing region, and now the colors intensify. Greens first, vibrant, flowing, shimmering like silk in a breeze. Then reds above them, faint and haunting like the afterimage of a sunset seen through frosted glass. Blues flicker at the lower edges, playful and quick, while purples ripple outward in veils so thin you feel you could breathe them in. You're floating in a world made entirely of moving light, soundless yet full of presence. And then something strange. You hear a whisper, not with ears because there's no air up here to carry sound, but with something else, a sensation, a faint crackle like static brushing your skin. A quirky tidbit auroras may actually produce faint audible sounds, soft hisses or pops detected by microphones on the ground during strong displays. Some researchers think the sounds form when geomagnetic disturbances induce electrical discharges near Earth's surface. It's not a proven mechanism, but it makes the northern lights feel even more alive. Scientists still argue whether auroras truly create atmospheric sounds or whether humans just want the night sky to talk back to us. The debate is more poetic than scientific, and honestly that's half the charm. You drift deeper into the auroral glow, letting the magnetic funnels guide you like handrails made of light. The electrons rushing past you collide with atoms below, and the sky erupts into shimmering waves. Curtains ripple side to side, arcs grow brighter, spirals form, shapes expand and dissolve like living smoke. You're inside a cosmic lantern show, drifting through the world's slowest fireworks. The magnetosphere funnels particles into the auroral ovals on both poles, so while you float near the north, a matching dance unfolds over the south. Earth is wearing two glowing crowns at once, quiet, majestic, and never precisely the same twice. Below you, the atmosphere thickens just enough to catch the particles. Every collision emits light. Every light fades, replaced by another. Waves pulse in long, sweeping motions. You get the distinct feeling that if you reached out, your hand would pass through the lights like through water, cool, soft, shimmering. You look up toward space and the colors seem to flow upward like reverse lightning. You look down toward Earth and the light spills across the darkness like luminous rivers. Snowy landscapes below reflect the glow, turning entire regions ghost green for a moment before fading back into shadow. And then come the arcs. Sometimes auroras bend and coil into huge crown-like shapes that span half the sky. Other times they snap from dim to brilliant in seconds, a phenomenon known as a substorm, when magnetic tension stored in Earth's magnetotail suddenly releases. It feels like the sky taking a deep breath and exhaling all at once. Another light joke enters your mind: if Earth had a screensaver, auroras would absolutely be the default setting. As you drift through the glowing sheets, you feel the pull of the magnetosphere shifting again. The flow of particles is never steady. It pulses, surges, fades. The magnetic field lines guide everything, but also twist unpredictably with solar conditions. Sometimes the aurora thickens into bright crackling ribbons. Sometimes it dissolves into wispy silent clouds. Scientists still argue how much of auroral structure is shaped by solar wind conditions versus internal magnetospheric dynamics. The aurora is like weather. It follows rules, but only partly, and it loves to surprise you. You cross through a particularly bright patch of green, the light flickering like fire seen through swirling mist. Electrons stream past, spiraling along field lines. Some particles accelerate so fast they release X-rays when they hit the atmosphere, a reminder that this beauty is also power. You descend just enough to see the curvature of Earth beneath the glowing lights. Continents sleep quietly below, unaware that above them the sun's breath is painting masterpieces in the sky. And you realize this auroras are the Earth's quiet way of singing back to the sun. Not in words, not in sound, in light. You drift forward, letting the glowing curtains fade behind you, rising once more into the upper magnetosphere. The shimmer remains below like a warm memory. Ahead, the wind calls you toward a world where beauty didn't win, where the solar wind stripped and hollowed a once livable atmosphere. Mars is waiting. You leave Earth's glowing curtains behind, drifting once more into the open flow of the solar wind. The shift is immediate, like stepping from a cathedral filled with stained glass shimmer into a wide, empty desert glowing with invisible heat. The wind pulls you outward through the curvature of the Parker spiral toward a world that once held onto its atmosphere with pride and then slowly lost it to the very breath of the sun you're now riding. Mars. You sense it before you see it, a dip in magnetic pressure, a hollowness like walking into a room missing its doors and windows. Mars does not greet the solar wind with a global magnetic shield. Instead, it offers a patchwork of crustal magnetic remnants, scattered pockets of ancient magnetism frozen into rocks billions of years old. They stand like tiny magnetic ruins, incomplete and unable to form a planetary fortress. A mainstream fact, Mars once had a strong global magnetic field similar to Earth's, but its core cooled early, switching off the dynamo. With no magnetic protection, the solar wind began stripping its atmosphere molecule by molecule. You drift closer and feel the solar wind intensify, not because it's stronger here, but because nothing pushes it back. It flows freely, plunging toward the Martian atmosphere with barely a shiver of resistance. You feel the impact region ahead, the induced magnetosphere. Unlike Earth's elegant magnetic globe, Mars' magnetosphere is a distorted temporary solar wind-shaped bubble, created only because the charged particles of the sun charge the upper Martian atmosphere and sweep around it. It's reactive, not defensive. Think of it less as armor, and more as someone holding up a backpack to block a water balloon. The bow shock ahead is softer here, ragged at the edges. The solar wind slams into Mars' ionosphere and generates a shock wave, but it's weaker, flickering, unstable. You pass through it like slicing through fog. No sharp transition, just soft turbulence and drifting ions. Then you feel the oxygen ions escaping from Mars' upper atmosphere pulled away by the solar wind. Long, faint trails drift behind the planet like gossamer ribbons being unspooled. You follow one, watching how the solar wind catches the ions and carries them off into space molecule by molecule. A quirky tidbit, the MAVEN spacecraft detected atmospheric sputtering at Mars, where high-energy particles knock atmospheric atoms into space like billiard balls ricocheting off each other. Mars is being sandblasted by the sun. You drift toward the dayside ionosphere, and that's where the stripping becomes intimate. The solar wind digs in, carving away neutral particles that have just been ionized by sunlight. Oxygen escapes, carbon dioxide escapes, hydrogen from ancient water escapes. You feel the slow, patient loss, the trickle of a world leaking breath. Scientists still argue how fast Mars lost its atmosphere, whether the escape was steady over billions of years, or punctuated by violent episodes during solar maximums or young sun superflares. Evidence hints at both, but the timeline remains a cosmic puzzle. You move closer to the crustal magnetic patches, odd little oases of magnetism frozen into the southern highlands. They're tiny compared to planetary scales, but up close they're astonishingly strong. You drift above one and feel the magnetic field twist sharply, pulling solar wind particles aside, forming miniature auroras just above the Martian surface. These patch auroras flicker without the need for a global field, tiny green glows produced when electrons collide with atmospheric gases directly above magnetic anomalies. They're rare, hidden and hauntingly beautiful. Mars has no bright curtains like Earth, no sweeping sky ribbons, but it has these small, shy ghosts of what once was, auroral freckles, traces of a magnetic soul long extinguished. You drift over Mars' terminator line where day meets night, and feel the temperature drop as the thin atmosphere leaks heat almost instantly. Without a magnetic field and thick air, Mars' surface is exposed to cosmic rays and ultraviolet radiation. The solar wind grazes it directly, carving at the atmosphere like a chisel. Another light joke forms quietly in your head. If planets had skincare routines, Mars skipped sunscreen and is now paying for it. You float into the night side, induced magnetotail, long, wispy, fragile. Here the solar wind drags behind Mars a long ribbon of ionized gas, a tail shaped almost like a comet's. Every so often, magnetic reconnection tears pieces of this tail away, sending atmospheric flakes drifting into space. You follow the tail outward for a moment, feeling how easily the solar wind carries it off. You imagine all the water Mars once had, rivers, lakes, maybe oceans slowly broken apart by sunlight, the hydrogen escaping upwards, stolen by the wind. The sun's breath turned Mars from a watery world into a dry husk, and yet Mars continues to breathe weakly, but persistently. Its atmosphere still tries to resist. Dust storms rise, some so enormous they engulf the entire planet for weeks. Dust becomes charged influences. The ionosphere affects how the solar wind interacts with the planet. Even now, Mars fights back in its own dusty way. Scientists still argue whether Mars' atmosphere might be partially regenerated by volcanic activity deep underground, or whether it's in an irreversible decline. MAVEN data suggests instability. Mars is still changing, still reacting, still negotiating with the solar wind. You drift away from Mars now, pulled again by the outward flow of the solar wind. Behind you, the red world shrinks, still glowing with its faint patches of magnetic defiance. Ahead of you lies a world even more extreme in its relationship with the sun. Venus, a planet with no magnetic shield at all, yet somehow still clinging to an atmosphere 90 times thicker than Earth's. A cosmic paradox wrapped in sulfuric clouds, and you're drifting straight toward it. You drift onward from Mars, letting the solar wind pull you back into its steady outward exhale. The red planet shrinks behind you, its thin atmosphere, its patchy magnetic scars, its long escaping tail fading into the background. Ahead, the next world waits like a glowing ember wrapped in poison clouds, a world that took the sun's breath full on the chin, and somehow refused to be stripped bare. Venus. If Mars is the lesson in what losing a magnetic field can do, Venus is the lesson in how bizarrely different outcomes can be even under the same cosmic wind. You feel the pressure shift as you approach. The solar wind doesn't flow freely here, but not because Venus pushes it back with magnetism. Oh no. Venus fights the sun with chemistry and electricity instead of a planetary magnetic shield. A mainstream fact, Venus has no global magnetic field. None. Its core spins too slowly or too differently to power a dynamo. Yet its atmosphere is so thick, 90 times Earth's pressure, that it reshapes the solar wind into a bow shock anyway, using charged upper layers of the atmosphere as a kind of electrically active shield. You feel the bow shock ahead, sharper than Mars but stranger. It doesn't form around a magnetic bubble, it forms around the ionosphere itself because the upper atmosphere becomes ionized by intense sunlight. You drift through it and feel the sudden deceleration of plasma as the solar wind slams into charged layers of gas. It's like hitting an electrified pillow. Soft somehow, yet unyielding. Then you enter the induced magnetosphere of Venus. This one is different. Broad, blunt, and thick. No internal magnetic field shapes it, so it flows outward based purely on how sunlight ionizes the top of the atmosphere and how the solar wind pushes against that electrically charged layer. You drift lower, and the ionosphere becomes intense. Sunlight strips electrons from nitrogen and carbon dioxide, turning the region into a glowing shell of charged particles that wraps the entire planet. It's a strange sensation, like floating above a vast invisible trampoline of electric potential. And here comes the paradox. The solar wind does strip particles from Venus. It does blow away oxygen and hydrogen. It does chip at the atmosphere. But Venus loses mass incredibly slowly, because its atmosphere is absurdly thick. A quirky tidbit: even though Venus has no magnetic field, it loses atmospheric particles at roughly the same rate as Earth, a paradox scientists love to bring up whenever someone says magnetic fields are the whole story. You drift along the dayside ionosphere, feeling a pulsing electric field sweep across the region. Venus has what's called a double-layer, two sheets of charged particles, separated by a voltage difference that's strong enough to accelerate ions upward into space. This electric field is so powerful that it's been nicknamed the Venusian electric wind. It can strip oxygen ions away even without solar storms. Imagine an invisible hairdryer blowing oxygen into space 24/7. Scientists still argue whether this electric wind alone could strip an ocean's worth of water over billions of years, or whether solar storms were the main culprits. Venus probably once had water, but now it's as dry as a cosmic bone. You drift toward the terminator, the line between day and night, and feel the electric fields change direction. The night-side ionosphere collapses, almost entirely falling back into neutral gas, with barely any charge left. The solar wind curls around the planet and forms a magnetotail. Yes, even without a magnetic field, Venus has a tail shaped by the wind's flow. You follow that tail now, drifting behind the planet. The solar wind pulls charged particles outward, forming long filaments that stretch into space behind Venus like glowing ribbons. Some of these ribbons carry ionized oxygen, the last crumbs of what may once have been ocean water. A soft, dark thought edges into your mind: if Earth lost its magnetic field, this could be its future. But that's a worry for another night. You drift back toward the planet's night side, feeling faint magnetic ripples created entirely by the solar wind itself. Venus's upper atmosphere generates little pockets of induced magnetism through a process called magnetic draping. The solar wind's own magnetic field gets bent around Venus like fabric stretched over a ball. It's thin, weak, but real. You hover for a moment above the nighttime clouds, sensing the turmoil below. The atmosphere is thick enough to crush a submarine, hot enough to melt lead laced with sulfuric acid, and blanketed with lightning storms so powerful they light up the upper clouds like slow, silent fireworks. If Earth's auroras are calm silk-like curtains, Venus's atmospheric electricity is a swamp of constant low-frequency flashes. Another light joke sneaks out. Venus is like that friend who says, "I don't need protection, I'm built different and against all odds" is absolutely correct. You drift upward again, following the ionized layers as they interact with the solar wind. The sun's breath pushes hard here, shaping the ionosphere into a blunt-nosed comet-like structure. The flow splits around the planet and reconnects behind it in a long tail, just like it did at Mars, but thicker, denser, hotter. Yet Venus doesn't lose its atmosphere the way Mars did, because Venus's atmosphere is a fortress made of gas. It's so dense that even the solar wind can't meaningfully erode it. Instead, the wind reshapes it, sculpts it, charges it, electrifies it, but it cannot blow it away. Not yet. Scientists still argue whether Venus had a magnetic field early in its history, and whether losing it doomed the planet, or whether its slow rotation and runaway greenhouse feedback loop sealed its fate regardless. Most models agree it was once more Earth-like than not. But today, Venus is a lesson in how solar wind chemistry, rotation, and temperature can combine into something that looks familiar and alien at the same time. You drift past the last edge of Venus's induced magnetotail, where the solar wind resumes its steady spiraling push outward. Behind you, the yellow-white planet glows beneath its acid clouds, a world that somehow stays whole, without the shield every other rocky planet envies. Ahead, the solar wind grows turbulent again because your next destination isn't subtle. Jupiter is waiting, and its magnetic field is so massive It makes Earth's look like a refrigerator magnet stuck to a Titan's shield. You drift away from Venus's glowing acid-wrapped world and slip back into the sun's exhale. The solar wind stretches out before you again, wide, swift, spiraling gently, but even from here you can feel a new presence on the horizon. Something huge. Something magnetic. Something so oversized that the solar wind itself seems to slow down a little, as though bracing before hitting a wall. Jupiter. Not just the biggest planet in the solar system, but the owner of the largest, most absurdly muscular magnetic field of any world within billions of kilometers. If Earth's magnetosphere is a protective bubble, Jupiter's is a fortress. A monstrous swollen shield so large it would appear bigger than the moon in our sky, if it emitted visible light instead of radio waves and X-rays. You feel it before you reach it. Not as a pressure change, but as a magnetic gravity, a tug on the plasma around you, a sense of entering a massive domain long before the planet itself comes into view. A mainstream fact, Jupiter's magnetosphere extends up to 7 million kilometers toward the Sun and stretches more than 600 million kilometers behind it. That's nearly the distance from the Sun to Saturn. Jupiter doesn't just have a magnetosphere, it has a magnetic empire. As you glide closer, the solar wind begins bunching up ahead of the giant planet. The bow shock forms an enormous curved wall of compressed plasma, like the wake of a colossal ship pushing through a cosmic sea. You drift through the shock and everything shifts. The wind slows dramatically, becoming turbulent, compressed, almost frustrated. Then you enter the magnetosheath, the chaotic zone between shock and shield. But this one isn't like Earth's or Mars or Venus. No, Jupiter's magnetosheath feels like entering a stadium-sized thundercloud made of charged particles. The turbulence is intense. Magnetic waves slam into each other like slow-motion tsunamis. Electricity hums through the plasma like 1,000 choir voices warming up. And then the magnetopause. It is without exaggeration immense. You touch the boundary and it feels rigid, thick, almost like a wall. The solar wind hits it and struggles. Jupiter's magnetic pressure is so strong, it can hold back storms that would flatten Earth's magnetopause like a soda can. You pass inside the magnetosphere and the environment transforms instantly. Everything becomes structured, ordered, powerful. The magnetic field here is so dense and so dominant that even the solar wind loses its personality and becomes a visitor in someone else's kingdom, a quirky tidbit. Jupiter's magnetic field is about 20,000 times stronger than Earth's at the planet's cloud tops. If you had a metal implant, this place would yank it out of your body like a frustrated dentist. And the scale. Oh, the scale. You drift deeper, and suddenly something else appears, ribbons of plasma glowing faintly. They wrap around Jupiter's equator in a torus shape, a giant donut of charged particles encircling the planet like an electrified halo. This is O's plasma torus, fed by volcanic moon, Io, the most volcanically active body in the solar system. Every eruption blasts sulfur dioxide into space where Jupiter's magnetic field strips it into ions and flings it into the torus. The result is a glowing reactive plasma ring hundreds of millions of kilometers across. Scientists still argue the exact mechanisms that accelerate these Io-sourced particles to nearly relativistic speeds. Some say plasma waves. Others blame magnetic reconnection. A few point fingers at rotating electric fields driven by Jupiter's monstrous magnetosphere. You drift along the torus feeling ions whipped into circles so fast they would vaporize anything foolish enough to get close. Being here is like floating inside a particle accelerator the size of a solar system. Then you reach Jupiter itself, not the planet, but its magnetic heartbeat. You don't see Jupiter yet, but you feel its rotation. The planet spins once every 10 hours, dragging the magnetic field along with it. This fast rotation turns the magnetosphere into an immense swirling engine. Plasma is flung outward like water from a spinning wheel. Electric currents surge along magnetic field lines. Jupiter becomes not just a planet, but a generator. You drift closer to Jupiter's auroral regions, the most powerful auroras in the entire solar system. They burn constantly, even without solar wind input, because Io's plasma torus pumps energy into the magnetic poles non-stop. The auroras here are so bright they emit X-rays. They're enormous, fixed, roaring loops of energy that dwarf Earth's delicate curtains. You see them now, blazing ovals at the poles, brighter than welding arcs stretching thousands of kilometers. This isn't sky painting, this is sky scorching. Electric currents stream downward in colossal beams, Particles slam into Jupiter's upper atmosphere and ignite it in a furious glow. Even here, drifting safely away, you feel the vibration, the electric hum, the power. A light joke enters your mind. If Earth's auroras are candlelight, Jupiter's are stadium floodlights. Someone forgot to turn off. You drift into Jupiter's magnetotail now. It stretches far into space, sometimes beyond Saturn's orbit. Inside, the magnetic field twists into ropes and sheets, storing vast amounts of energy. When reconnection happens here, the result isn't a gentle auroral substorm, it's a planet-sized magnetic tantrum. Scientists still argue whether Jupiter's reconnection events are driven mostly by solar wind pressure or by the internal engine created by Io's plasma supply. The truth is, probably both. Like most big cosmic arguments, the answer sits annoyingly in the middle. You drift outward, feeling Jupiter's magnetic grip loosening. The solar wind begins to reassert itself. The Parker spiral whispers against your back once more. Behind you, Jupiter fades, still monstrous, still powerful, still wrapped in a magnetic storm so relentless that entire spacecraft have been fried just by getting too close. Ahead, a quieter giant waits, a world of icy beauty and subtle magnetism. Rings, shadows, delicate plasma dances. Saturn is calling, and its rings shimmer in the solar wind like frost illuminated by starlight. You drift out of Jupiter's magnetic empire, shaken loose from the grip of a field strong enough to twist plasma into knots and illuminate the poles with X-ray halos. The solar wind returns gradually, first as a whisper, then as a steady push, then as the familiar gentle current guiding you outward again. For the first time in a while, space feels spacious. And ahead of you, forming out of the background like a pale flattened halo, Saturn appears. Not the planet, not yet, but its rings. At first they look like a single smooth plane faintly glowing, a thin blade of light slicing across your field of view. But as you drift closer, the rings sharpen into countless band strands and filaments, icy dust arranged with such precision it feels sculpted. And in a way it is, because the solar wind sculpts them too. The rings aren't static ornaments, they're alive in their own quiet, particulate way. Micrometeoroids pepper them, plasma flows across them, light charges them, dust dances, electricity builds. The solar wind interacts with them constantly, and you're about to drift into the most delicate battlefield in the solar system. A mainstream fact is Saturn's rings are made mostly of water ice pieces ranging from tiny grains to boulders the size of houses. But they hold electric charges, and the solar wind influences how they clump, drift, and even glow. As you approach, the particles become visible not individually but as a thin, shimmering haze. Tiny ice grains scatter sunlight like powdered diamonds. The solar wind hits them and knocks electrons loose. Suddenly every grain becomes a little charged body, repelling some neighbours, attracting others, shifting minutely in the dance. You slip into the plane of the rings, gliding through a region where the particles are sparse enough not to pose danger, but dense enough to feel like drifting through an icy fog. The sunlight flickers, shadows from ring particles ripple over you like the dappled shade of leaves on a breezy day. The solar wind reaches this region and reacts strangely. Saturn's magnetic field bends some of it, but the rings charge and discharge like giant capacitors. On the day side, ultraviolet light creates a positively charged upper layer. On the night side, electrons rush back in, flipping the charge. The rings breathe electrically as they orbit into day and night, a quirky tidbit. The rings produce their own neon-like glow in ultraviolet light, a faint ghostly radiance that spacecraft have captured, turning the ring system into a cosmic blacklight poster if you know how to look. You feel the charge shifting as you glide through the dusty plain. Some ice grains tug toward you, others drift away. Everything is governed not just by gravity but by electrostatic forces so delicate they would never matter on a planet's surface. Scientists still argue whether Saturn's rings are ancient, older than the dinosaurs, or incredibly young, maybe only 100 million years old. Newer observations suggest they might be slowly dissolving under the influence of the solar wind and Saturn's own magnetic field ring rain falling into the planet. The debate burns on. You drift over the B-ring region, where particles pack more densely. Shadows deepen. Variations in density form wave-like patterns, spiral density waves driven by Saturn's moons tugging. Gravitationally at the ring edges, they look like ripples on a pond frozen mid-motion. But the solar wind leaves fingerprints here too. The plasma flow interacts with the ring particles, charging them unevenly. Some regions puff up slightly vertical warping that looks like tiny hills of dust. Other regions flatten. Electric currents form along magnetic field lines, linking the rings to Saturn's upper atmosphere. In fact, you turn your awareness downward, and a surprise flicker greets you. Auroras from the rings. When charged particles from the rings funnel along magnetic field lines into Saturn's atmosphere, they produce ultraviolet auroras tied directly to ring material. You're seeing the cosmic equivalent of a neon sign powered by icy dust. A light joke drifts through your thoughts. Saturn is basically the solar system's most overachieving art student ring's auroras. Electromagnetic light shows the whole package. You leave the densest portion of the rings and drift toward the Cassini division, the famous dark gap that isn't actually empty. It's filled with finer, sparser dust shaped by the gravity of the moon mimas and sculpted by the solar wind's persistent nibbling. You pass through it feeling only the faintest grainy texture in the plasma. The solar wind flows more smoothly here, brushing past the dust like wind slipping through tall grass. Ahead, Saturn's magnetosphere unfolds gentler than Jupiter's, but vast-structured and elegant. Its magnetic field is remarkably aligned with its rotation axis, forming a smoother, more symmetric shield. But the rings influence it profoundly, creating charged regions nowhere else seen in the solar system. You drift into Saturn's magnetosphere, now sensing how the solar wind presses on it. The magnetopause is farther out than Earth's, but far more flexible, breathing in and out with solar storms. The rings sit entirely inside this shield, protected yet still sculpted indirectly by changing currents and fields. Scientists still argue why Saturn's magnetic field is so perfectly symmetric. Dynamo models predict it shouldn't be not to this degree. Something deep inside Saturn is cheating the physics exam, and nobody knows exactly how. You glide outward again, rising above the ring plane. The entire system spreads below you like a luminous vinyl record dropped into space grooves, etched by gravity and plasma. And the solar wind keeps blowing across it all, charging it, shaping it, whispering through the dust like a cosmic breeze through frost. Ahead, another oddball magnetosphere waits. One that doesn't face the sun straight on, one that tips sideways and spins like a falling coin. Uranus is next. A world that rolls through space, dragging its weird, drunken magnetosphere with it, and letting the solar wind carve patterns unlike anything else in the solar system. You drift outward from Saturn, watching the rings fade into a pale, shimmering line behind you like frost evaporating under a distant sunrise. The solar wind settles again into a steady outward pull, calm but insistent. Space grows quieter, colder, and yet ahead something feels off. Not wrong, just tilted, skewed, as if the currents you're riding suddenly veer sideways, because they do. You've reached a world that rotates on its side and drags its magnetosphere along for the ride like a tipped umbrella spinning in a windstorm. Uranus. You sense it before you see the planet itself. The magnetic pressure ahead doesn't behave like it should. It twists oddly, misaligning with the solar wind's flow in ways your instincts weren't built to interpret. Earth's field meets the sun face first. Jupiter's field bulges outward like a proud chest. Saturn's is tidy, polite aligned. But Uranus shows up sideways, wearing a magnetic field that's tilted another 59 degrees relative to the planet's rotation axis, and offset from its core by thousands of kilometers. It's the cosmic equivalent of someone wearing a backpack on their stomach, a hat on sideways, and both shoes on the wrong feet. A mainstream fact, Uranus's magnetic field is so misaligned that as the planet rotates, its magnetosphere wobbles wildly, sweeping through the solar wind like a lighthouse beam doing somersaults. You drift closer, and the solar wind reacts in real time to the planet's confused geometry. The bow shock ahead is malformed, not a smooth barrier, but a rippling asymmetric wall. The solar wind slams into it, forming eddies and waves more chaotic than anything you've encountered so far. It's like watching the Parker spiral trip over a misplaced rug. You pass through the bow shock and the turbulence feels tangled. The solar wind slows unevenly. Magnetic pressure varies chaotically. Pockets of plasma swirl unpredictably as if the flow is trying to decide which direction around Uranus actually is. Inside the magneto sheath, the plasma becomes even more disordered. You drift through regions where the magnetic field strength spikes, then collapses, then flips direction entirely. Nothing here is symmetric. Nothing is predictable. The planet's magnetic field rotates rapidly beneath you. dragging the entire magnetosphere into a weird lopsided cartwheel. You finally reach the magnetopause, the outer boundary of Uranus's magnetic domain, and it feels slippery, flexible, almost gelatinous. As the planet rotates, the magnetopause inflates and collapses in cycles, sometimes pointing toward the sun, sometimes away, sometimes sideways. It's a magnetic pogo stick, a quirky tidbit. Because Uranus is tilted sideways, its magnetic poles sweep in huge circles each day. This means the front and back of the magnetosphere keep changing places. The solar wind has no stable structure to push against, so it reacts like a confused cat watching a laser pointer. You slip inside the magnetosphere, and immediately you sense two competing forces: Uranus's rotation fast, just 17 hours, the solar wind's direction steady outward from the sun. The clash between them twists the magnetosphere into a corkscrew shape, especially during solstice. Field lines stretch, snap reconnect in ways that resemble tangled holiday lights more than any neat planetary structure. Scientists still argue whether the Uranian dynamo lies in a thin icy shell or a slushy mantle of water-ammonia fluid. The magnetic field appears to originate far from the core, which breaks most classical dynamo rules. Uranus is basically the astrophysical student who refuses to turn in assignments, but still inexplicably passes the class. You drift along one of the magnetic field lines, if line even applies. It bends, kinks, then swoops dramatically as it reconnects with solar wind fields. Reconnection events here aren't gentle mergers. They're violent flips that can switch the entire magnetosphere from open to closed configuration in one rotation. You sense a huge lopsided magnetotail dragging behind Uranus, twisted like a long ribbon caught in a vortex. The tail spirals as the planet rotates, forming structures scientists have described as corkscrew shapes hundreds of thousands of kilometers long. It feels alive, restless, chaotic in an oddly soothing way. A light joke drifts through your mind. If magnetic fields had personalities, Saturn would be the neat freak, Jupiter the gym bro, Earth the responsible parent, and Uranus the eccentric artist who paints while upside down. You approach the region where Uranus's faint auroras form far weaker than those of planets with strong magnetic fields but still real. They flicker at odd places, sometimes nowhere near the magnetic poles because, well, the poles aren't where they're supposed to be. The auroras glow mostly in ultraviolet, dim and patchy, reacting more to the solar wind than to the planet's rotation. They feel shy, uncertain, like they're trying to perform but the stage keeps moving. You drift past the night side, feeling the magnetotail twist into spirals. Reconnection events here can send plasma storms backward, sideways or diagonally directions that don't even have names in standard magnetospheric physics. Scientists still argue how Uranus interacts with the solar wind during equinox versus solstice. During solstice, the magnetic poles face almost directly at the sun for prolonged periods, creating bizarre configurations where the solar wind can access the planet's polar regions continuously. Some models suggest constant reconnection, others suggest none at all. Uranus continues spinning sideways beneath you, dragging its tipped magnetic field around like a carnival ride that forgot safety regulations. The solar wind flows against it, over it, through it, forming structures no other planet can produce. You let the outward flow carry you again, leaving the wobbling magnetosphere behind. Ahead, the sunlight grows a little dimmer, the wind thins slightly, and another ice giant waits beyond the horizon, Neptune. Similar on paper, but its magnetic mischief is a different story altogether, where Uranus lists Neptune dances, and you're drifting straight toward its deep blue sway. You drift onward from Uranus, letting the crooked, tumbling magnetosphere fade behind you like a strange dream, one of those dreams where gravity forgets how to behave and doors open into the wrong rooms. The solar wind steadies again, grateful to be free of the magnetic chaos. You feel the current strengthen just a little, flowing more cleanly, more predictably, and then you sense it. Another magnetic presence ahead. Not as bewildering as Uranus's sideways lurch, not as clean as Saturn's symmetry, not as overwhelming as Jupiter's brute strength. Neptune. Cold, deep and mysterious. A planet whose magnetic field doesn't tilt drunkenly like Uranus's, but slips off-center and off-kilter in its own elegant, unpredictable way. You feel the distortion before you see the planet. The solar wind veers, slows and curls subtly, at first, then distinctly, like a stream bending around a submerged stone, whose shape it can't quite understand. Neptune's magnetosphere is misaligned by about 47 degrees, an offset from the planet's center by thousands of kilometers. If Uranus is the cosmic jester, Neptune is the magician who performs tricks you don't fully catch. A mainstream fact. Neptune's magnetic field is not centered on the planet. It's shifted significantly northward, meaning part of the magnetic bubble is much thicker and stronger than the opposite side. As you drift closer, the bow shock forms ahead, but unlike Uranus's, which was messy and angled, Neptune's bow shock is surprisingly crisp, strong, defined. The solar wind slams into it and piles up in a thick glowing plasma front. You slip through it and feel the sudden deceleration like walking into a blast of cold air that freezes your breath mid-step. Inside, the magneto-sheath turbulence dances, not frantic like Jupiter's, not irregular like Mars, not deeply chaotic like Uranus's. Neptune's turbulence has rhythm. Waves form, break, reform. There's a pulse to it, a slow heartbeat carried by plasma. You ride the flow deeper until the magnetopause rises before you, and Neptune's magnetopause feels smooth, almost polished. It curves around the planet like a drifting bubble, though not quite centered. The solar wind splits and slides around it, and you can feel the elegant tension between the outward push of the wind and the inward force of Neptune's magnetic field. You slip inside, and Neptune's magnetic domain greets you like entering a spacious, dimly lit ballroom, quiet, blue-toned, and full of slow-moving currents. The sun's breath no longer dominates. Neptune's own magnetic architecture takes over. And what strange architecture it is. You sense the off-center field pulling stronger in some regions, weaker in others. Magnetic lines bunch tightly on one side of the planet and spread loosely on the opposite side. It gives the magnetosphere an asymmetric drifting feel, as if it's shifting slightly with every rotation, a quirky tidbit. Neptune's magnetic poles wander so far from the planet's geographic poles that auroras form in unexpected places, sometimes near the equator. You glide toward those auroral regions, now dim ultraviolet ovals, faint compared to Jupiter's blazing stormlights or Earth's bright curtains. Neptune's auroras are softer, almost ghost-like. They're more influenced by solar wind conditions than by internal processes. You can feel the dependency, the way each spark of light corresponds to a subtle ripple from the sun. Scientists still argue what drives Neptune's magnetic asymmetry. Some models suggest the dynamo operates not in the core, but in a shell of partially ionized water-ammonia slush. Others argue the offset indicates complex flow patterns in a superionic ocean, one that behaves like both solid and liquid at once. Neptune's interior is basically a physics fever dream. You drift deeper into the magnetosphere, following a field line that curves outward toward the tail. Neptune's magnetotail stretches far behind it, twisting into a long, spiraling ribbon, less chaotic than Uranus's, but still distorted. As the planet rotates, its offset magnetic field sweeps the tail into a corkscrew pattern, giving it graceful twists and subtle oscillations. You feel one of those oscillations now, a gentle magnetic tremor that ripples along your path. It feels like the slow sway of waves under a boat, rhythmic and oddly relaxing. A light joke surfaces. If Neptune hosted a spa, its magnetosphere would be the deep tissue massage package, gentle pressure, slow waves, maybe a complementary algae wrap. You drift past faint plasma structures, patches of energetic ions, threads of charged particles, small regions of enhanced magnetic strength. These pockets shift as Neptune rotates like candle flames flickering in a draft. The deeper nightside tail stretches thinner and thinner, interacting with the solar wind in subtle, complex ways. Reconnection events here are quieter, more meditative than Jupiter's explosive tantrums. When the sun's field links with Neptune's, you feel soft snaps, small flips in direction, gentle shifts that barely register, except as slight whispers in the plasma. Scientists still argue whether Neptune's magnetic field reverses or merely oscillates in long cycles. Voyager 2 data hinted at drifting polarity patterns, but with only one flyby in history, the truth remains wrapped in deep blue mystery. You drift outward, leaving the magnetosphere through a region where Neptune's influence fades slowly rather than sharply. The solar wind seeps back in like water filling a draining tide pool. Behind you, Neptune glows faintly, a distant sapphire orb spinning quietly in the dark. Its magnetic field sways gently around it like a loose cloak caught in a breeze. Ahead, the solar wind thins noticeably. The particles spread farther apart, the pressure drops, and at the frozen edge of sunlight's power, a tiny world waits barely touched by the wind, barely resisting it, barely holding on to its own breath. Pluto, a world so small and fragile that the solar wind turns it into something almost comet-like. And you are drifting toward it now. You drift farther outward, and the solar wind begins to feel thin. Not weak, just stretched like taffy pulled across billions of kilometers. The density drops. The pressure eases. The current softens around you until it resembles more of a suggestion than a flow. You've reached a region where the sun's breath doesn't dominate so confidently anymore. A place where the wind still blows, but gently, almost shyly. And at this frontier floats a small, cold world whose atmosphere hangs on by a thread. Pluto. You sense it before you see it, not as a magnetic push or a strong field, but as a softening of the solar wind, a looseness. The wind doesn't hit Pluto, it merely brushes past it, grazing lightly over the thin envelope of gas that flickers around the dwarf planet like a whisper. Pluto's atmosphere, when it has one, is fragile, temporary, fickle. A mainstream fact, Pluto's atmosphere is made mostly of nitrogen, with traces of methane and carbon monoxide, and it expands when the planet is close to the sun, then freezes and collapses onto the surface as it drifts toward aphelion. You drift in close now and feel that delicate boundary. Unlike Earth or Jupiter or even Mars, Pluto has no bow shock, no magnetic armor, no dense ionosphere to hold back the sun's breath. The solar wind glides right and gently compresses Pluto's atmosphere and then drags pieces of it away in a long faint tail. You follow that tail for a moment. Its gossamer thin stretched behind Pluto like a silk ribbon so faint it barely exists. This is Pluto's atmosphere escaping into space, molecule by lonely molecule. A quirky tidbit, New Horizons discovered that Pluto has two distinct atmospheric escape modes, one slow and jeans-like molecules drifting off, and another that behaves more like a comet's tail irons being swept off by the solar wind. The planet is basically torn between being a tiny world and a tiny comet. You drift closer again, feeling how the solar wind interacts with the hazy halo. The particles barely notice the planet's presence. They don't form a strong shock. Instead, they gently flow around Pluto's upper atmosphere, nudging nitrogen ions along with them like a breeze pushing dandelion seeds. Scientists still argue whether Pluto ever generated a magnetic field in its early history. New Horizons didn't detect one, but that doesn't rule out a tiny dynamo long dormant. If it once had one, it's long gone now. Today, Pluto is defenseless, not in danger, just exposed. You hover above the limb of the dwarf planet and the atmosphere glows faintly blue, delicate ethereal. Not aurora blue, not earth sky blue. A pure scattering haze, sunlight dancing through layered microparticles, in a thin shell that looks unreal in the blackness. Think of it as the faintest cosmic halo, the universe's softest watercolor stroke. Even the solar wind seems hesitant to disturb it. You drift downward, skimming just above the upper atmospheric fringe at around 1,500 kilometers altitude. Here the molecules are so sparse you could wait hours before colliding with one. But their presence is unmistakable. They shimmer, they glow, they respond. You can feel the nitrogen being ionized by solar UV light. The newly charged particles feel the tug of the solar wind immediately swept outward, starting their journey into the tail. It's a quiet, continuous leak, Pluto exhaling into space. Another light joke sneaks in. If Pluto were a person, it would be that friend who says I'm fine while slowly drifting out the door wearing a cardigan 2 sizes too big. You drift above the night side now. The temperature drops dramatically. Some atmospheric layers collapse downward, freezing onto the surface as bright nitrogen frost. The pressure plunges. The solar wind barely touches the dark side, there's nothing left for it to touch. But the escaping tail still flickers behind Pluto, illuminated faintly by sunlight, like a dim cosmic contrail. You follow the tail outward until it dissolves entirely into the thinning solar wind. Out here, everything fades. Pluto's influence is small, fragile, beautiful in its transience. Scientists still argue how thick Pluto's atmosphere becomes at perihelion, and how completely it collapses near aphelion. Some models say it nearly disappears. Some say it never fully freezes out. New Horizons caught Pluto in a warm phase, but the next atmospheric collapse is likely underway right now, far beyond the reach of our telescopes. You drift back toward the front side of the dwarf planet, watching sunlight skim across its ridges, ice plains and deep shadows. The solar wind brushes over it lightly, barely registering the encounter, because out here the sun's breath grows thin. Very thin. So thin, in fact, that you can feel the beginning of a transition, the solar wind spreading wider, its particles more spaced, its pressure lower. You're approaching a region where the sun's exhale weakens enough that the galaxy begins to push back. Pluto is the last world meaningfully shaped by the solar wind. Beyond this point, the sun's breath becomes a whisper. Ahead lies the vast, quiet, mid-heliospheric plain, where the solar wind stretches itself so much that it begins to lose control, a region where the flow thins, slows and cools, a region where the solar system becomes soft, porous, diffuse. You drift onward, feeling the wind grow weaker with every kilometer. The great edge approaches, but for now you float on, carried gently by the last strong breath of the sun. You drift away from Pluto's faint blue haze, and almost immediately the environment around you begins to loosen, like stepping from shallow water into a vast, quiet ocean. The particles thin out, the wind softens, even the Parker spiral's confident curl starts to feel stretched and weary. You're entering a region where the sun's breath grows thin, very thin. The solar wind is still here, still flowing, but it's no longer the bright, energetic gale you met near the corona. No longer the structured breeze that carved magnetic bubbles or slammed into planetary shields. Here the particles are so sparse that you could drift for minutes and not feel a single ion brush past. And yet the wind still moves steady outward, faithful. A mainstream fact: by the time the solar wind reaches around 30-50 astronomical units, its density has dropped to just a few particles per cubic centimeter, thousands of times thinner than any vacuum humans can create on Earth. You feel that thinning now, not as emptiness, but as gentleness. The solar wind's pressure decreases and its speed fluctuates more noticeably. Even the temperature drops as the plasma spreads out, losing energy through expansion. You're riding the sun's breath at its most vulnerable, its most fragile, its most stretched. A quirky tidbit: despite being stretched so thin, the solar wind here still moves faster than 1,000,000 kilometers per day. It's just relaxed about it. Like a jogger who's given up on the race but refuses to stop moving entirely. You drift through the mid-heliospheric plain, and the spiral structure behind you looks almost straight now. The magnetic field lines are pulled taut like long thinning ribbons fluttering in slow motion. They wiggle from distant turbulence, carrying the faint whispers of storms launched years ago when the solar cycle was in a more dramatic mood. You sense those ancient storms, tiny pressure waves, faint ripples. Some of them originated before Pluto's last perihelion. Others began when smartphones were still a novelty on Earth. Out here, space carries decades of solar memories. Scientists still argue how turbulence evolves at these distances. Some claim the solar wind becomes smoother the farther out it flows. Others insist it becomes more chaotic, riddled with small-scale irregularities. Voyager data suggests both may be true depending on particle type and magnetic environment. Space as usual refuses to pick a lane. You drift deeper, and something subtle shifts. The solar wind begins slowing, not dramatically, not sharply, but steadily. The sun's breath is losing its strength. You look ahead, and you don't see a wall or barrier. You see nothing unusual at all, but you feel the growing resistance, the pressure from beyond, the gentle push of atoms, ions, and magnetic fields that don't belong to the sun. The interstellar medium, the gas and magnetic haze between stars, provides a counterwind. The solar wind doesn't dominate anymore, it negotiates. And as you move forward, you feel that negotiation intensify. The sun pushes outward, the galaxy pushes inward. The boundary between the two grows closer, but you're not there yet. You drift through regions where the solar wind becomes patchy, uneven. Some areas show pockets of slightly denser plasma relics, of past solar storms that haven't fully dissipated. Other regions feel stretched thin enough to snap. If plasma could sigh, the solar wind would be exhaling its last long breath before reaching its limit. You pass through small bubbles left behind by turbulence remnants of magnetic reconnection events far upstream. They drift like cosmic tumbleweeds, slowly rotating, slowly fading. Out here, even turbulence moves with a contemplative pace. A light joke pops into your mind. If the solar wind were a person, this would be the moment it says, "I think I'm good to just coast from here." Particles around you now are cold, by heliospheric standards, tens of thousands of degrees instead of millions, which sounds ridiculous until you remember that plasma temperature doesn't feel like air temperature. It's really a measure of particle speed. And these particles are far slower than their younger cousins closer to the Sun. You pick up hints of interstellar neutrals drifting in atoms from outside the solar system that sneak through the heliosphere and become ionized by sunlight. These pickup ions begin to mix with the solar wind, adding mass and changing its character. You can feel their presence as subtle bumps in the flow. Scientists still argue exactly how pickup ions affect the solar wind's eventual slowdown. Some models show they absorb energy and hasten the compression. Others suggest they stabilize the flow. The truth once again has the audacity to be complicated. You drift onward, feeling the solar wind weaken further. It's still blowing, still outward. But the pressure difference between the inside and outside of the heliosphere is shrinking with every kilometer. You sense the approach of a vast invisible cushion ahead, a region where the solar wind will slow abruptly, a region Voyager 1 compared to flying into thick syrup after years of thin air, the termination shock, where the sun's breath finally loses its supersonic confidence and collapses into slow subsonic flow, where the solar wind thickens again not because of the sun but because it's being squeezed, where the heliosphere begins to realize it is not infinite. The edge of the solar system doesn't start with a wall, it starts with a slowing, a soft resistance, a quieting of the wind. You drift toward that quieting now, every movement bringing you closer to the great drawn-out sigh of the sun. Ahead lies the shock that ends the solar wind's long free ride, and you're moments away from entering it. You drift toward the invisible resistance ahead, and the solar wind around you continues to stretch thin, so thin that each particle feels like a lonely traveler wandering through a nearly empty universe. The flow is still outward, still constant, but the confidence in its direction has started to falter. There's a softness creeping into the current, a sluggishness. You're approaching a boundary where the sun's breath can no longer outrun the pressure from the galaxy. The termination shock. You don't see it, but you sense it like you would approaching weather front and atmospheric weight, a shift in the wind's character, a subtle tightening of the space around you. The solar wind is still supersonic here, still racing outward faster than the speed at which pressure disturbances can travel. But that can't continue. Ahead, the interstellar medium pushes back just enough that the solar wind must slow down, must yield. A mainstream fact, Voyager 1 crossed the termination shock in 2004 at about 94 astronomical units from the Sun. Voyager 2 crossed it in 2007 at 84 AU. The boundary isn't fixed, it expands and contracts with the solar cycle like a breathing skin. You drift closer and the solar wind grows turbulent, not violently, just busy. Like a crowd slowing from a run to a walk. Pickup ions, those once neutral interstellar atoms that got ionized inside the heliosphere, are everywhere now. Tens of millions of them per cubic kilometer bouncing around chaotically inside the thinning solar wind. They steal energy from the flow, warm the plasma, and create micro instabilities that make the wind wobble, like a poorly tuned guitar string. Scientists still argue how exactly pickup ions shape the termination shock. Some say they make it thicker and more diffuse, others say they create multiple small shocks. Voyager data suggests the shock is not a thin, crisp boundary, but a wide rumbling region with layers like a cosmic speed bump stretched over millions of kilometers. You can feel the beginning of that rumble now. The Parker spiral behind you straightens slightly as the flow slows. The magnetic field lines tangle. The solar wind speed fluctuates, dropping from hundreds of kilometers per second to just a few dozen. Temperature rises not because the particles heat up from sunlight, but because their random motion increases after the shock. You feel the moment the wind hits the interstellar pressure. It's not a wall, it's not even a sudden jolt. It's a soft thickening, like drifting into fog that pushes back. Then a subtle compression, a ripple, a shudder through the magnetic field. You've crossed the termination shock. Everything around you changes. The solar wind slows abruptly to subsonic speeds. The plasma density spikes. Pickup ions swirl in chaotic orbits, scattering the flow. Magnetic turbulence grows in tense waves, colliding, merging, tearing apart. It's like drifting into a cosmic soup pot stirred by invisible hands. The region is louder, metaphorically speaking. Plasma waves hum like deep bass notes. Magnetic oscillations vibrate your awareness. It feels like being inside a constantly shifting drumhead. A quirky tidbit, Voyager 2 detected literal magnetic hums in this region, low-frequency waves produced by turbulent interactions between solar and interstellar plasmas. If you could convert them to audible sound, they'd resemble a deep, haunting rumble. You drift deeper into the shock layer. The sun's breath here is hot, hundreds of thousands of degrees, and its particles move chaotically, randomly directionless. Supersonic order has dissolved into turbulent subsonic drift. The solar wind has lost the race. Scientists still argue whether the termination shock is spherically symmetric or shaped like a long-tailed windsock. Some models show it squashed on the upwind side and stretched into a comet-like shape on the downwind side. Voyager crossings suggest an uneven, lumpy boundary with ripples larger than planets. You feel one such ripple now, a wave of magnetic pressure that passes through you like a slow seismic tremor. It doesn't push violently. It rolls steady and strong, rearranging plasma as it goes. Then you drift outward past the densest turbulence into a region where the solar wind's chaos begins to settle again. The flow is slower, warmer, denser. You've entered the subsonic swell, the place where the solar wind limps outward, no longer expanding freely but being pushed back by the galaxy. Here the motions are thicker, heavier. Particles drift without direction. The sun's influence wanes, not gone, but muted like music heard through a wall. The shock behind you was the last gasp of speed. Ahead lies something stranger. The heliosheath, a vast turbulent buffer zone where the sun's breath and the galaxy's whisper wrestle quietly for dominance. This region is enormous, tens of billions of kilometers thick and more mysterious than any other part of the heliosphere. Even Voyager's data barely samples it. You drift toward it now. The wind is slower, the magnetic field is tangled, the pressure grows, and the edge of the sun's influence begins to flicker on the horizon like the faint glow of dawn before a storm. You drift into the heliosheath, and immediately the environment feels heavier, not like gravity, but like the air before a thunderstorm. The particles around you move slowly, erratically caught between competing forces. The solar wind has lost its speed. The interstellar medium hasn't yet taken over. Everything here exists in a kind of cosmic stalemate, a borderland where nothing is settled and everything is in motion. This is the heliosheath, the sun's vast, turbulent hinterland. Behind you, the termination shock recedes into memory, a slowdown, a compression, a rumbling shift that mark the end of the solar wind's long free run. Ahead, the heliopause, the boundary between the sun's influence and the galaxy's waits somewhere in the distance, shimmering uncertain and constantly changing shape. Between these two boundaries lies chaos. Beautiful, sprawling, magnetic chaos. A mainstream fact, the heliosheath is filled with hot, subsonic solar wind that has been slowed, distorted, and heated by the termination shock. It's a region so turbulent that Voyager spacecraft detected wildly fluctuating magnetic fields, sudden pressure spikes, and unexpected particle flows that defied predictions. You drift through the thick, warm plasma. The pressure feels different, less like a wind, and more like drifting through the slow, underwater currents of an invisible ocean. Plasma waves ripple around you. The magnetic field lines twist, kink, and loop. Some regions feel compressed, others stretched thin. It's messy, but not random. There's pattern hidden in the turbulence, structure inside the chaos. Scientists still argue exactly what drives the strange bubble-like features inside the heliosheath. One model suggests that the sun's magnetic field breaks into countless magnetic bubbles, small rounded structures that trap particles inside. Another model claims these bubbles merge and form giant cells like slow-moving honeycomb patterns. Both models have evidence. Neither is fully convincing. You drift into one of these magnetic cells now. The feeling is unmistakable. The magnetic field strengthens around you, forming a soft cage. The plasma inside moves slowly in rolling eddies like gentle tides, sloshing inside a closed pool. You can sense the boundaries, the edges feel firmer, more structured. The bubble shifts, expands, contracts. You move with it. A quirky tidbit, these magnetic bubbles may act like cosmic filters, letting some particles escape the heliosphere while trapping others for long periods. Imagine a room full of revolving doors, each deciding particle by particle who leaves and who stays. You drift out of the bubble and into a region where the magnetic field suddenly weakens. The temperature shifts, the density changes. This is the thing about the heliosheath, nothing stays consistent for long. It's a giant pot of simmering plasma stirred by magnetic tension, buffeted by interstellar pressure, and heated by the sun's fading breath. You feel a wave, an actual pressure wave, roll through the region. It travels outward from the sun at hundreds of kilometers per second. This could be the imprint of an old solar storm one launched years ago that's only now arriving here. Voyager detected such shockwaves multiple times, giant solar eruptions that took a decade to reach the heliosheath. When they arrive, the entire region vibrates. You feel that vibration now, a low, slow thrum, the soundless equivalent of a giant drumbeat in the magnetic field. Scientists still argue how far these shockwaves propagate. Some believe they continue all the way into interstellar space. Others think they dissipate at the heliopause. But Voyager data suggests the shocks don't always behave consistently. They strengthen, weaken, split, merge. More complicated than expected, less cooperative than hoped. You drift through a region where the magnetic field lines straighten for a moment, drawn tight by pressure from outside the heliosphere. Beyond the heliosheath lies the interstellar medium, a thin soup of gas, plasma dust and magnetic fields belonging not to the sun but to the galaxy itself. Its pressure presses inward, shaping the heliosheath like hands pressing on a balloon. You feel that pressure now, a faint inward push. The solar wind pushes outward. The galaxy pushes inward. The balance is delicate, shifting, alive. A light joke drifts into your mind. If the solar system had a front porch, the heliosheath would be the lawn where the sun and the galaxy politely argue about property lines. You drift deeper. The sun feels far away now, so far that its light is dim to a cold gleam. The solar wind still flows but weakly, like the last breath of a runner nearing the finish line. The magnetic field is messy, tangled and sluggish. Pickup ions swirl like lazy bees, and then you sense it. A subtle change. A boundary that isn't a wall, isn't a line, but a shift, a new texture in the plasma. The solar wind's identity begins to blur. Neutral atoms from the galaxy seep in. Energetic particles drift with no allegiance to the sun. Magnetic fields from the Milky Way press closer. You're approaching the heliopause. But the heliopause is not a crisp shell. It's a region broad, uneven, alive, where the sun loses influence molecule by molecule, magnetic line by magnetic line. Scientists still argue whether the heliopause has holes where interstellar particles flow in freely, or whether it behaves like a wrinkled membrane constantly shifting under external pressure. Voyager 1 and 2 crossed it in different locations with starkly different conditions, proving that the boundary isn't smooth or uniform. But that's ahead. For now, you float through the heliosheath, a place of tangled magnetic weather, strange currents and slow warm plasma that carries the last heartbeat of the solar wind. Ahead lies the edge that isn't an edge, a boundary defined not by walls but by competing breaths, the sun's final exhale and the galaxy's quiet inhale, and you are moving closer with every drifting moment. You drift forward deeper into the heliosheath's shifting currents, and the turbulence begins to soften, not becoming calmer exactly, but becoming different. The plasma ahead feels neither fully solar nor fully interstellar. The magnetic field lines waver, stretch and blur into patterns that no longer match the Parker spiral. The sun's breath is still present, but kneeling, its authority slipping. You're entering the edge that isn't an edge, the heliopause. But unlike any boundary you've crossed so far, this one refuses to present itself cleanly. There is no sharp line, no sudden change like stepping from sand to pavement. Instead, the space around you begins to feel ambiguous. Direction becomes less meaningful. Flow becomes subtle. Pressures delicately balance, shift and rebalance. You sense two forces now, the faint outward puff of the sun's wind, the equally faint inward murmur of the interstellar medium. And the region between these dueling breaths feels like an invisible trembling membrane. A mainstream fact, the heliopause marks the boundary where the outward-moving solar wind drops to zero speed relative to the sun and is replaced by the plasma of the interstellar medium. But the exact location and shape of this boundary fluctuate constantly with solar activity. You drift closer, and the solar wind becomes ragged, patchy, sluggish, fragmenting into islands of plasma separated by odd, quiet pockets. The magnetic field strengthens from the outside, pressing inward in a slow, steady creep. You feel the structure tightening, compressed from both directions. The heliosheath behind you pushes outward. The galaxy ahead pushes inward, the boundary in the middle. It quivers, Scientists still argue whether the heliopause acts like a porous membrane allowing neutral atoms to pass through, or whether it behaves more like a wrinkled sheet flapping in a slow cosmic breeze. Voyager's data suggests both. In some places the boundary is sharp and clean, in others it seems to leak, distort and ripple. You sense a ripple now. A magnetic wave sweeps across you, slow, wide, persistent, compressing and releasing the plasma around you, like the rise and fall of a calm but powerful tide. Then gradually the turbulence quiets, the temperature changes, the particle motion shifts orientation. You have entered the transitional sheath, the inner edge of the heliopause itself. Here everything feels contradictory. The magnetic field becomes stronger but more stable. The plasma becomes thinner but more organized. The motion of particles becomes gentler but more foreign. The solar wind's identity unravels while the interstellar medium's identity emerges. You drift through a region where neutral hydrogen from the galaxy slips in freely. These neutrals ignore magnetic fields entirely, gliding across boundaries as if borders don't exist. When sunlight ionizes them, they join the solar wind as pickup ions, creating complex flows that neither the sun nor the galaxy fully controls. A quirky tidbit: some of these neutral particles come from stars light years away. In a very real way, atoms from other suns are drifting into the solar system right now, brushing past your imaginary fingertips. You float deeper, and the solar wind fades even more. The plasma temperature cools dramatically, a coolness that doesn't feel thermal but conceptual, like the environment is shedding the last warmth of solar influence. Even the sun feels farther away now, dimming into something more symbolic than physical. Then a shift, not a jolt, not a wall, just a moment where everything aligns differently. The magnetic field changes direction. The solar wind speed relative to the sun drops to nearly zero. Cosmic rays increase sharply, no longer deflected by the sun's long magnetic reach. Voyager 1 reported this sudden spike in cosmic rays as the moment it entered interstellar space. You feel that spike now, a wash of high-energy particles streaming freely where the sun can no longer block them. Scientists still argue whether this spike marks the true crossing or just a partial breach. Voyager 2 crossed in another region and saw a different signature. The heliopause, it seems, is an inconsistent host. You drift onward through the final layers of this boundary. The plasma density increases again, but this time because of the interstellar medium pushing inward, not because of the solar wind pushing outward. The magnetic field tightens, firming into a stable orientation shaped not by the sun, but by the broader flow of the galaxy. You've crossed the heliopause, but there was no sudden glow, no dramatic frontier moment, no cosmic road sign reading "You are now leaving the solar system." Instead, the transition felt like walking into a different room in the dark, not because the floor changed, but because the air did. Behind you, the sun's breath stretched thin. Ahead, the quiet pressure of interstellar space. You are now drifting in an environment shaped not by the star you know, but by the spaces between stars. The solar system hasn't ended, it simply stopped being the dominant presence. Ahead lie faint drifting atoms of hydrogen and helium, cosmic dust, magnetic currents from ancient supernovae. A river of starlight formed long before the sun was born, and somewhere out here, tiny aging spacecraft are still whispering faint messages home. Their paths are waiting for you next. You drift in this new quieter medium, no longer the solar wind's domain, but not yet the true bloodstream of the Milky Way either. Interstellar space here feels like a subtle shift in gravity, or the moment when you step outside and realize the humidity has changed without warning. Everything is cooler, calmer, heavier, in a soft, enveloping way, and somewhere ahead, gliding through this strange borderland like tiny metal ghosts, are the first human-made objects ever to leave the sun's protective breath. Voyager 1 and Voyager 2. You don't see them yet. You feel them, thin strands of radio whispers stretching back toward Earth, carrying news from a place no person has ever stood. You turn toward the faint signal like a plant turning toward sunlight. The magnetic field out here is steady, aligned not with the sun but with the broader flow of the galaxy. The plasma is denser than in the inner heliosphere, thin by Earth standards, but richer than the post-shock solar wind. Cosmic rays pepper the darkness, drifting freely now that the sun's shielding field is weak. And then you sense it. A small metallic presence cutting through the calm like a stone gliding silently across a pond. Voyager 1. The farthest human-made object in existence. A mainstream fact, Voyager 1 crossed the heliopause in August 2012, becoming the first spacecraft and the first object from Earth to enter interstellar space. It detected the change not by seeing stars differently, but by hearing the sudden rise in cosmic rays and the shift in plasma vibration. You drift closer to its imaginary track, feeling the gentle oscillation of its plasma wave detector, the instrument that hears vibrations in the interstellar gas like a cosmic seashell pressed to its metal ear. Voyager cannot see the boundary, it cannot smell it, touch it, or taste it, but it can listen. The tones here are deep and slow, long wavelengths, thick textures like the low hum of a distant cello. The spacecraft rode out a massive solar shockwave in 2021, years after the sun belched it outward, and the plasma around Voyager responded with vibrations you can feel now, like the ripples of a galaxy's heartbeat. A quirky tidbit, those plasma vibrations were converted into audio that humans can hear. The sound is eerie, a rising whistle, the voice of interstellar space itself captured from tens of billions of kilometers away. You drift up alongside imagined Voyager 1, its golden antenna forever pointed back toward Earth. The spacecraft is old, running on the fading warmth of radioactive decay. Its instruments flicker with time, its systems shutting down one by one as power drops. But it still speaks, a faint radio whisper taking over 22 hours to reach Earth. You drift around it in a slow arc, feeling the contrast between this tiny metal relic and the immense quiet of the interstellar medium. Scientists still argue exactly how interstellar this region really is. Some claim Voyager is just beyond the heliopause but still inside a transitional buffer shaped by the Sun. Others say it's fully outside, feeling the pressure and flow of the Milky Way's magnetic field. The truth is blurred like the heliopause itself. You let Voyager 1 fade behind you and drift toward another presence. Not far away in cosmic terms though, still separated by billions of kilometers, Voyager 2 follows its own path. Voyager 2 crossed the heliopause in November 2018, 6 years after its sibling. But it entered through a different region with different conditions, proving once again that the heliopause is not a clean edge but a wrinkled membrane. You sense its approach before seeing it. Voyager 2's instruments are still healthier. It carries a magnetometer, so it detected the heliopause more directly. You feel the moment of crossing as a sharp, noticeable twist in the magnetic field, the cleanest signature humans have ever recorded of leaving the Sun's domain. You drift alongside Voyager 2, sensing its movement through slightly denser plasma. Its detectors still taste the slowed interstellar solar wind mixing with the true interstellar medium. Its instruments still hear faint plasma tones. Together, Voyager 1 and 2 map the shape of the Sun's fading breath, and you drift with them through a region where the Sun is no longer king, merely a quiet star among many. A light joke surfaces. Two tiny spacecraft running on 1970s hardware have traveled farther than any billionaire, any astronaut, any future tourist ever has. Interstellar space belongs to machines that have less computing power than a modern toaster. The interstellar medium grows richer as you continue past the Voyagers. Hydrogen atoms drift here like slow-moving ghosts of ancient stars. Interstellar dust, tiny grains of carbon and silicates flickers faintly as they slide past. Cosmic rays surge stronger, no longer blocked by the Sun's magnetic field. You feel them, sharp, old, wandering for millions of years before brushing past you now. The Sun behind you is still visible but tiny, just another point of light surrounded by a thin bubble, no longer sufficient to keep out the galaxy. You drift further outward. The solar wind behind you thins to nothing. The galaxy begins to hum louder. New patterns emerge in the plasma patterns shaped by forces older than the solar system itself. Ahead lies a strange glowing structure, a compressed wall of hydrogen lit by the collision between the Sun's breath and the galaxy's whisper. It shimmers softly in the distance, and you are drifting straight toward it. You drift onward through the calm of interstellar space, letting the Voyagers fall behind you like distant memories. Two tiny sparks carrying humanity's message in bottles into an ocean so large it barely notices. The Sun is smaller now, a pale pinprick nestled inside its faint inflated bubble of influence. The solar wind has thinned into nothing. Cosmic rays from every direction pass by freely, no longer blocked or pushed aside. But ahead, very faint at first, you feel pressure. Not forceful, not sudden, just thicker, like stepping from cool air into humidity. This is the hydrogen wall, a region where the interstellar medium and the solar wind collide so subtly, so delicately, that hydrogen atoms build up into a faint glowing barrier, one that Voyager instruments hinted at, and global radio telescopes have chased like a whisper in the dark. You drift closer, and the pressure changes again. Even the magnetic field feels different, tighter, cleaner aligned not with the sun's wounds or planetary quirks, but with the broader flow of the galaxy. You've left the tangle of the heliosheath behind. The plasma here moves with more dignity, more order, is the signature of interstellar space itself. A mainstream fact, the hydrogen wall is created when neutral hydrogen in the interstellar medium slows down as it encounters the outward pressure of the heliosphere. This creates a region of compressed heated hydrogen detectable through Lyman alpha light. You sense that light now. It isn't bright nothing like a star or nebula, but it has a texture, a faint shimmering warmth in the fabric of space. The wall feels like a veil, thin but resistant. It's not solid, you can pass through it without a sound. But the density is higher here than in the surrounding interstellar medium, not by much, maybe 10–30%, enough to feel like the universe briefly stops to inhale. Neutral atoms drift past you in thickened pools. Some are slowed by the sun's outward push. Others flow around the heliosphere like water deflecting off a rock. You sense interstellar hydrogen sliding along the boundary in long, languid arcs. Scientists still argue how thick the hydrogen wall actually is. Some models say it spans dozens of astronomical units. Others think it's incredibly thin and patchy. The Voyagers detected hints of increased density, but they couldn't see the full structure. Much of what we know comes from ultraviolet observations taken from Earth and from the Hubble Space Telescope. You drift inside the wall now, and the temperature rises slightly, not heat you could touch, but kinetic energy in the hydrogen atoms. They vibrate, bump, and scatter with subtle grace. This region feels like the warm skin where two cosmic rivers press against each other. A quirky tidbit, some scientists believe the hydrogen wall might glow faintly in ultraviolet, making it one of the only large-scale structures illuminated by sunlight at the very edge of the solar system. If your eyes could see ultraviolet, this place might shimmer like a pale lavender mist. You drift deeper, letting the thickened hydrogen flow around you. Behind you, the heliopause remains a shimmering memory, a magnetic membrane stretched thin across light years. Ahead, the true interstellar medium begins to dominate. The sun's influence is mostly symbolic now, carried only by faint magnetic threads that stretch outward like aging spiderwebs. You pause well, as much as anything can pause while drifting through plasma, and feel the subtle tug of the galaxy. Here you begin to sense the gentle wind of the interstellar medium itself, a slow flow of gas and dust drifting past the heliosphere as the sun moves through the galaxy at about 230 kilometers per second. To you, that flow feels soft and steady, ancient, a breeze older than our star. It carries atoms forged in other suns long before the sun existed. Some were created in supernova millions of years before Earth even formed. Others were ejected from red giants or flung out by cosmic collisions. You're drifting through a river of cosmic ancestry. A light joke wanders through your thoughts. If ancestry tests worked on atoms, most of the ones around you would need family trees bigger than the periodic table. You drift farther outward. The hydrogen wall begins to thin again. The density relaxes, the flow smooths. You've passed through one of the last interactions between the heliosphere and the galaxy. Behind you lies the sun's entire domain, a vast bubble blown by the solar wind across billions of kilometers. Ahead of you lies the genuine interstellar medium, a sea of hydrogen, helium dust, and magnetic fields stretching between the stars like a cosmic ocean. And somewhere out in that ocean are isolated islands of plasma shock fronts from ancient supernova remnants, and the faint gravitational wakes of passing stars. You're leaving the solar system not with a bang, not with a sudden threshold, but with a slow exhale into the deep. The solar wind has faded into a memory. The interstellar medium stretches ahead, quiet, endless, ancient. And the galaxy prepares to welcome you into its broader, colder arms. You drift away from the hydrogen wall, watching it fade behind you like a pale bruise in the fabric of space, soft, faint, and strangely comforting. As you move farther, the last hints of the sun's breath unravel completely. No more solar wind particles racing past. No more Parker spiral tugging at your awareness. No more magnetic trembling from heliospheric turbulence. You're outside. Truly outside. This is not the emptiness people imagine when they hear interstellar space. This is a medium, a real one, quiet, thin, ancient, but alive with motion. The interstellar medium. It is made of ghosts, hydrogen atoms forged in long-dead stars, helium older than the Milky Way's spiral arms, dust grains carrying carbon ice iron, cosmic rays travelling since before humans discovered fire, magnetic fields twisted by supernova shockwaves. You feel all of it now, a slow drift of material flowing past you at the speed of the sun's journey around the galaxy. A mainstream fact, the solar system is currently travelling through a region called the local interstellar cloud, a warm, diffuse, partially ionized cloud that spans about 30 light-years. Its density is low, but still many times higher than the heliosheath. You sense that cloud now. The interstellar plasma is colder, gentler, but steadier than the solar wind. It flows with direction, not radiating outward like a star's breath, but sweeping uniformly past you, shaped by the galaxy's magnetic field and the sun's motion through space. You can feel that motion, the sun cutting through the local cloud like a ship through calm water. The flow of interstellar atoms drifts from your left to your right, slow but continuous like a cosmic breeze sliding through an endless night. You breathe it in metaphorically. It feels ancient. Scientists still argue exactly how thick the local interstellar cloud is, and whether the sun will exit it in tens of thousands of years or linger for much longer. It's a cosmic guessing game shaped by extremely sparse data. You drift deeper, letting the galaxy's magnetic field wrap around you. It feels different from the sun's field, more stable, more uniform, more stretched, like lines painted across the Milky Way's lanes of gas and dust. These fields were shaped by ancient supernova explosions, by the rotation of the galactic disk, by the slow drift of charged particles over millions of years. A quirky tidbit, some scientists believe the magnetic field of interstellar space can redirect dust grains like tiny cosmic compass needles, aligning them in the same direction. If you could zoom in on a dust mote here, it might be pointing the same way as trillions of others. You move farther from the heliosphere and something subtle shifts inside you. You feel the sun receding, not physically but influence-wise. It's no longer the shaper of your environment. Here the sun isn't king. It's just one star among billions. You turn your awareness backward, trying to sense the heliosphere. It's still there, a faint bubble glowing in your perception. But it's already a distant shape, the sun's fading breath trapped inside. Ahead of you, the interstellar medium grows richer, if rich is the right word for something so thin. The density here may be only 1/10 of a particle per cubic centimetre. But compared to the void inside the heliosphere's outskirts, it feels like drifting into waist-high water. You raise your attention upward. Well, the direction is meaningless here, but the thought still feels correct, and sense faint ripples in the interstellar magnetic field. These ripples are remnants of ancient shock waves, the leftovers of stars dying explosively millions of years ago. Their energy is diluted but not forgotten. Cosmic rays stream past you, high-energy particles, from sources scattered across the galaxy. Some were launched by supernova remnants. Others come from black hole accretion disks or magnetars. A few might be travelers from entirely unknown sources. You feel them pass like needles of pure energy, sharp but not painful. A light joke surfaces. If the solar wind was a gentle afternoon breeze, interstellar space is the old grandfather who quietly sits on the porch and occasionally throws cosmic ray peanuts at you for fun. You drift farther still, listening to the background hum of the galaxy. This hum isn't sound. Space doesn't carry sound, but a texture in the plasma, a vibration in the magnetic field, a rhythm in the cosmic rays. It's faint, but steady. Scientists still argue whether this hum owes its origin mostly to supernova-driven turbulence, or to the Milky Way's slow rotation and large-scale magnetic structure. Voyager data points to both. The galaxy is a complex musician playing overlapping notes across millions of kilometers. You move through the slow flow of interstellar atoms, and you begin to sense structures ahead. Filaments of denser gas, magnetic folds, weak shock boundaries, interstellar dust lanes drifting like smoke in zero gravity. You can't see them, but you feel the difference in pressure and magnetic tension. The sun's presence behind you is now faint, just a small bubble, glowing softly in the dark, carried along inside the galactic flow, like a paper lantern drifting down a river. You let yourself be carried too. For the first time, your environment is shaped not by the sun, but by the Milky Way itself. You're no longer exploring the solar wind. You're drifting through the galaxy's quiet breath, And ahead, merging gradually with the interstellar current, a strange twisting structure waits one that might tell you where the heliosphere is headed next. A boundary not of the sun's making, but of the galaxy's architecture. A fold in the cloud, a change in density, a hint of where the sun will travel in tens of thousands of years. You drift toward it now, slow, quiet, steady, letting the galaxy itself draw you deeper. You drift deeper into the interstellar medium, leaving behind even the faintest trace of the sun's breath. At this distance, the solar wind is not just irrelevant, it's forgotten. Its particles, once swift and full of heat, have slowed into silence. Its magnetic fields, once dominant, have faded into a ghostly afterthought. The Parker spiral, that elegant sweeping signature of the sun's rotating heart, barely has any presence here. It dissolves behind you like chalk dust blown from a teacher's hand. Now the environment belongs to the galaxy, and ahead lies a subtle but important structure and interstellar weather pattern. A shift in density, temperature and magnetic alignment. A place where the sun is heading in the far future. You're approaching the boundary between two clouds in the local interstellar environment. The local interstellar cloud is behind you, now thinning. Ahead lies the G cloud, cooler, denser and more mysterious. You feel the transition beginning. It starts as a soft rise in particle density. Not abrupt, just a steady increase, like walking into deeper water one step at a time. A mainstream fact, the sun moves through the galaxy at about 230 kilotons, and in 10,000 to 100,000 years it is expected to transition from the local interstellar cloud into the G cloud. Both are warm, partially ionized gas structures shaped by ancient supernova. You drift into the overlap region, a murky, blended boundary, where the properties of the medium begin to change. Temperatures drop slightly. The magnetic field shifts direction, rotating ever so subtly. The density increases from perhaps 0.2 atoms per cubic centimeter to around 1 atom per cubic centimeter, still unimaginably thin but meaningful on cosmic scales. You can feel this density change like a faint pressure against your awareness. Scientists still argue whether the boundary between these clouds is smooth or sharp. Some data suggests a gradual blending zone. Other measurements hint at sudden transitions. The truth seems to depend on direction, and the Milky Way rarely provides tidy answers. As you drift farther, faint filaments of neutral hydrogen slide past you like long strands of invisible silk. Some are denser pockets shaped by shock waves from supernova remnants millions of years old. Others are remnants of ancient interstellar turbulence. Interstellar dust grains appear now, still rare but more common here than inside the heliosphere. Carbon-rich grains, silicate flakes, tiny icy fragments. Many are coated in organic molecules, the byproducts of cosmic chemistry that has run quietly for billions of years. You imagine one drifting past your shoulder, a microscopic speck that has travelled across half the spiral arm before brushing close to you. Some grains have passed near supernovae, been heated by starlight, then cooled in shadowy pockets between clouds. A quirky tidbit, some interstellar dust particles contain nanodiamonds, tiny diamonds formed in the fiery atmospheres of carbon-rich stars. Space literally pelts passing travellers with microscopic jewellery. The galactic magnetic field grows stronger here, more coherent. It threads the interstellar medium like vast steel cables running between stars. They shape how dust moves, how gas flows, even how cosmic rays propagate. You feel the field align around you like a gentle but firm current lifting upward. The sun will feel this field too when it eventually enters the G cloud. Its heliosphere might compress. The hydrogen wall may brighten. The solar wind's boundary might shrink. You drift deeper into the new cloud's influence. Temperatures dip slightly, but the plasma feels more energetic. Cosmic rays are more numerous, drifting in long, slow arcs, shaped by magnetic gradients. You sense faint shock waves, weak but discernible traces of long-dissipated supernova blasts. Scientists still argue whether the local interstellar cloud and the G cloud are fragments of a larger supernova-blown bubble. Some believe the sun is floating inside a vast cavity created by multiple ancient explosions. Others argue for a more gentle origin involving slow cloud evolution. You can feel the remnants of those explosions in the way the gas around you is arranged. Filamentary, patchy, sculpted by forces long spent, and now as you drift farther, you encounter something unexpected, a region where the temperature rises slightly, even as the density continues to increase. This transitional warmth isn't from stars, it's from friction, the subtle heating caused when the sun's motion through the medium generates turbulence and compression in the cloud's front edge. The sun is effectively ploughing through cosmic fog, producing a gentle bow wave. Not sharp enough to be a bowshock knot here where the sun's speed is subsonic relative to the local medium, but still a structure you can feel. The gas thickens, the magnetic field rotates further, dust grains become just slightly more common. Cosmic rays shift direction in measurable ways. A light joke flickers through your mind. You're now experiencing the interstellar version of moving from one internet provider's coverage zone into another. Same service, slightly different flavor, and nobody agrees where the boundary actually is. You drift still farther. The sun's fading heliosphere is now a distant bubble behind you, drifting like a lantern on a cosmic river. Ahead, the G-cloud begins to unfold in earnest. Strands of higher density gas weave through the darkness like invisible currents. Magnetic ridges form faint pressure arcs. Temperature gradients rise and fall gently like mountains worn down by time. You can feel that this region is not uniform. There are pockets of thicker gas regions of turbulence and calm open voids. It's a patchwork landscape without ground or sky. The galaxy is full of such cloud boundaries, such rivers of drifting hydrogen. The sun will cross many in its future. Each one will change the shape of its heliosphere. Each one will alter the solar wind's reach. Each one will leave a fingerprint on the cosmic weather enveloping our solar system. You drift through the threshold, now fully immersed in the next interstellar environment. The sun has done this before, and will do it again, and you adrift on this quiet cosmic breeze, follow it into its long future path. You drift deeper into the G-cloud, now fully leaving the warm, thinning embrace of the local interstellar cloud behind you. The space here feels subtly different, like stepping from one room into another identical room, but sensing the air pressure shift ever so slightly. Nothing dramatic, just a quiet change in the cosmic texture. Particles brush past you with a little more frequency. The magnetic field holds itself more tightly. And the interstellar medium begins to reveal long, faint structures, patterns shaped not by the sun, but by the galaxy's vast, slow, relentless dynamism. The G-cloud is cooler than the local interstellar cloud, but denser. Still thin by human standards, of course. 1 atom per cubic centimeter is laughably close to nothing, but on cosmic scales, density matters. Density shapes magnetic fields. Density shapes cosmic ray propagation. Density shapes how the sun's heliosphere will eventually compress as it plows into this new environment. A mainstream fact, the sun has been traveling through a complex network of interstellar clouds for the past 5 to 10 million years, drifting from one to another as these clouds ebb and flow. We just happen to live during a relatively quiet chapter in that voyage. You drift along with the galactic flow, letting the magnetic field twist gently around you. Here, the field is aligned differently than in the local interstellar cloud. It bends and arcs in long, smooth curves shaped by supernova remnants far away and by the galactic disk's rotational shear. These lines of force aren't static. They vibrate with slow waves. Alpha-Ven waves, magnetic ripples that travel through plasma like guitar strings plucked by distant explosions. You feel these ripples pass through you at long intervals, deep, soft, steady pulses. Scientists still argue how strong the magnetic field is in the G-cloud, and whether it will dramatically compress the heliosphere when the sun enters fully. Estimates vary widely. Some say the heliosphere could shrink by 30%. Others predict almost no change. For now, though, you aren't concerned with the future. The present is rich enough. The density increases slowly, not enough to impede anything, but enough that you can feel interstellar atoms brushing with more confidence. Some are neutral hydrogen, some are ionized hydrogen, a fewer helium, a fewer cosmic ray fragments, lone atoms blasted at high speed by past supernovae, and dust now noticeably more common. Tiny grains drift past you like flecks of ash in slow motion. Some are carbon-rich, some are silicate, some glint with thin coatings of ice, and some rare but real carry complex molecules, amino acid precursors, organic rings, carbon chains forged in the outer layers of dying stars. You float through a cosmic pantry of prebiotic chemistry. A quirky tidbit, interstellar dust grains occasionally stick together when cosmic rays crack their surfaces, forming fragile clusters that drift for millions of years before eventually entering star-forming regions. Some scientists believe dust grains like these seeded early Earth with organic material. You drift through a region where the magnetic field tightens, briefly strained by a nearby denser filament. That filament is long and narrow, shaped by a shock wave that occurred hundreds of thousands of years ago. Even now, the echo of that blast still shapes local space. You move alongside the filament for a while. It hums, very softly. Not a sound, not a vibration, more like a tension in the plasma, a slow wave traveling along its length. Scientists still argue whether such filaments are held together mainly by magnetic pressure, or whether they're relics of turbulence that simply haven't dispersed yet. Observations suggest a combination magnetic scaffolding wrapped around cold interstellar gas. You drift past the filament and back into the more diffuse part of the cloud. The galactic magnetic field stretches in broad arcs again. Cosmic rays thicken slightly, still sparse but more numerous than in the local interstellar cloud. Their presence feels sharper, more energetic, and somewhere in the distance, faint but unmistakable, you sense a dim, slow-moving pressure wave, a region where the density dips and rises over hundreds of astronomical units. It's a fossil imprint of a supernova shock front that passed through this region long ago. You pass into that fossil wave now. The temperature changes slightly. The density rises a hair. The magnetic field shifts orientation. A light joke drifts through your mind. You're riding the space equivalent of leftover ocean waves from a storm that ended before humanity existed. You drift onward, carried by the sun's galactic velocity. But then you feel something new, or rather something familiar but inverted. The galaxy's breath, not a strong wind, not a push, just a gentle pressure gradient and outward flow from a nearby hot bubble, where supernovae once carved a cavity through the interstellar medium. The sun is heading toward denser regions, but behind you interstellar gas flows away from the hot bubble, creating weak currents. You can feel these currents sliding across your path, soft, directional, full of the faint whispers of long-faded explosions. Scientists still argue whether the sun will eventually encounter fully cold, dense cloud material, capable of compressing the heliosphere dramatically, and possibly even letting interstellar particles reach Earth in higher numbers. Some models predict such encounters every few million years. Others think the sun's path will avoid the densest pockets. You drift through the G-cloud's internal currents, feeling how they shape magnetic fields like invisible hands kneading dough. The fields tighten, loosen, stretch, fold. You take a long, slow moment to look backward. The heliosphere, the entire region shaped by the solar wind, has shrunk into the distance. A shimmering bubble illuminated faintly by cosmic rays. It looks delicate now, small, precious. Ahead, the G-cloud continues, and beyond it, other clouds, other boundaries, other interstellar weather patterns waiting in the darkness. You drift forward through the soft galactic flow, sensing a new pressure change ahead, a faint thickening, a quiet gradient that hints at another subtle frontier. The sun is moving toward that frontier, and so are you. The galaxy is changing around you slowly, quietly, inevitably, and the sun's breath, so powerful near its face, becomes a humble whisper out here. Your journey toward the true fusion of solar and galactic winds continues. You drift farther deeper into the cloud, carried gently by the galactic flow, like a leaf swept along a slow-moving river. Behind you, the heliosphere, the entire bubble of the sun's breath, shrinks into a pale, shimmering shell. Out here it feels impossibly small. A tiny glow in an endless sea, a soap bubble floating between storms, but ahead you sense another shift. Not a dramatic boundary, not a shock front, just a soft rise in pressure. A subtle tightening of the magnetic field, a faint dip in temperature. It's the sign of yet another interstellar structure, a cooler, denser region part of the galaxy's patchwork of drifting clouds. This is the deep G cloud, a region the sun will move into tens of thousands of years from now. A place where the interstellar medium becomes richer, more textured, more alive with ancient echoes. The density rises slightly around you. Still incredibly thin, nothing you could ever feel physically, but on the scale of the galaxy, this is meaningful. Hydrogen atoms drift past in greater numbers. Helium mixes in. Dust grains appear more frequently, tiny flecks of cosmic history, drifting through the dark. A mainstream fact, these clouds are remnants of ancient supernovae, explosions that carved cavities, shaped magnetic fields, and left behind filaments of gas and dust that the sun now sails through on its long voyage around the galaxy. You drift into one of those filaments now, an elongated tendril of slightly cooler hydrogen. Its magnetic field is stronger than the surrounding gas, aligning itself like a taut rope. You sense its tension, its slow oscillations, the faint hum of energy stored inside. Scientists still argue how stable these filaments are. Some believe they last for millions of years. Others think they constantly form and dissolve as magnetic fields twist and turbulence reshapes them. Voyager data hints at changes too slow for a human life, but fast enough to matter over star lifetimes. You glide alongside the filament, feeling the coolness of its plasma. It isn't cold like ice, it's cold in the plasma sense, meaning particles move more slowly, carry less kinetic heat. You can almost feel the calmness of the region, like drifting into shade after sunlight. But the magnetic field here is strong. It pulls. It shapes the local space. It bends the pathways of cosmic rays. Cosmic rays hit you more intensely now, no longer shielded by the sun's vast magnetic bubble. High-energy particles from ancient supernova remnants, from distant black holes, from catastrophes so immense they reshape entire regions of the galaxy. They drift past in long, straight lines, as if nothing in the universe can stop them. Because out here, almost nothing can. A quirky tidbit, some cosmic rays have so much energy that a single proton carries the kinetic punch of a baseball pitch. Imagine being hit by that at nearly the speed of light. Thankfully, you're an imaginary narrator drifting in an imaginary plasma sea, so you can just shrug it off. You leave the filament and drift into a broader region. Pressure gradients shift. Magnetic fields rotate. The density rises again, then falls, then rises, like a tide with no shore. You're far beyond the reach of planets, stars, and winds. Gravity barely has meaning here. The sun's pull is little more than a gentle tug on the back of your shirt. You're drifting through the Milky Way's invisible architecture, its long drawn-out exhalations of ionized gas, its slow currents shaped by old scars. Scientists still argue whether the sun's heliosphere will survive every cloud it moves through. A particularly dense cloud, 10 times thicker than the one you're in, could crush the heliosphere inward, until its edge lies inside Earth's orbit. In such a case, cosmic rays could strike Earth far more intensely. Climate might shift. Atmospheric chemistry might change. But these are possibilities, not predictions. And right now you're drifting through a gentle region. Calm, structured, ancient. The galactic equivalent of a quiet forest clearing. You feel another shift. Slight but consistent. The magnetic field strengthens again, folding itself into arcs. This could be the beginning of another cloud boundary, a denser region, maybe even the precursor to the apex cloud, a mysterious cooler structure the sun is expected to encounter in the distant future. The density increases softly. The ions move slower. The dust grains become slightly more frequent. Not enough to call it crowded, nothing out here is crowded, but enough that you can feel the change in texture. You're now deep in a part of the galaxy shaped by overlapping shock remnants, interwoven fields and quiet flows of cold neutral gas. It's not empty. It's not uniform. It's not static. The galaxy breathes too. A light joke floats by. If space were truly empty, astronomers would have a lot more free time and a lot fewer headaches. You drift onward, letting the slow interstellar breeze carry you. Behind you, the sun's bubble glows faintly, still alive, still pushing, still, carving a tiny oasis out of the galaxy's chaos. Ahead, the Milky Way opens into wider, colder regions. The sun won't reach for hundreds of thousands of years. But for now, you're here at the very edge of the sun's reach, watching its breath fade into the greater breath of the galaxy. Your journey through solar winds, magnetic seas, interstellar clouds, and cosmic boundaries has brought you to this final outward horizon, the place where the sun's influence ends and the galaxy begins. And now, drifting quietly in the cool, slow currents of the Milky Way's interstellar medium, you begin your descent into sleep. Let everything slow now. Let the vastness around you stretch into something soft, something gentle, something dim enough that your own breathing becomes the loudest rhythm in the universe. The sun's voice is far behind you, a faint warm glow pressed into a distant corner of your awareness. You've traveled past planets and winds, past shocks and storms, past boundaries drawn not in lines, but in whispers and gradients. And now out here in this calm that belongs not to any star but to the galaxy itself, everything becomes quieter. The interstellar medium drifts around you, thin, cool, ancient. A slow-motion snowfall of atoms passing by on journeys that began long before the Earth existed. and will continue long after the last traces of humanity fade. You float among them unhurried, unbothered, like a feather lying on still water. Let the tension leave your shoulders. Let the muscles in your face loosen. Feel the edges of your thoughts soften like the way stars blur when your eyes begin to close. The magnetic field here is steady and simple. No storms, no sudden changes. Just a long, gentle flow shaped by millions of years of quiet cosmic motion. It wraps around you like a soft blanket, thin but infinite, cool but comforting. In this place, pressure gradients move like slow tides, guiding you without urgency. Every direction is safe. Every motion is gentle. There is nowhere you need to be, nowhere pulling you, nowhere calling. You're drifting in a space that has existed in calm for longer than you can imagine, and it welcomes you into its quiet rhythm. Let your breathing match it. Slow inhale, slow exhale. Let each breath feel like it moves along those broad magnetic arcs, unhurried, steady calm. Your thoughts begin to wander the way dust grains wander here, floating without weight, falling without direction. Let them drift. Let them lose structure, becoming soft impressions instead of sharp ideas. Let every image fade smoothly into the next. If a worry tries to surface, don't hold it. Just let it slide away like a neutral atom drifting past a magnetic ripple. Light, unattached, already on its way somewhere else. Let yourself feel small in the best possible way, not insignificant, but free. Freed from boundaries, freed from noise, freed from gravity itself. You're resting in a place where the galaxy hums softly, where nothing rushes, where even light takes its time. You're drifting in calm, you're drifting in safety, you're drifting in silence older than stars, and as your body grows heavier and your thoughts grow dimmer, let the last image you hold be simple, a slow river of starlight flowing past you, carrying you gently into the quiet of sleep. Thank you so much for keeping me company tonight. Don't forget to subscribe so we can share many more stories together.